Good morning, madam. Good morning.
Good morning, ma'am.
Madam, we are not able to hear you.
मैम क्या आवाज नहीं है क्या?
Can you hear me now?
Yeah. Now you are audible. So, Dr. Manish, you can start now.
Yeah. So, very good morning to all of our delegates and learners, beginners. We are very proudly privileged to be here, and a very fascinating time is now coming to an end. This is the last day of our short course, but I hope we will continue this group. We will keep sharing the thoughts, and our experts will be kind enough to guide us and remain in touch. Their blessings will also be with us, I hope. So, in this short course, very systematically arranged and well-connected lectures are presented, and we hope that these things will going to help us in even giving the investigatory projects for our UG and PG students. It will be a gateway for new challenging problems to us in this quantum world. We will be reconnected to the recent development in terms of educational research, in terms of knowing the nature better, and as far as today's lecture is concerned, we are with approximate methods. We have many methods of this kind to know the eigenvalues and eigenfunctions, but we have chosen variational methods in this course. There must be some hidden agenda about it. I'm keen to know about how it is beneficial, in what regards it will be beneficial as compared to WKB or the perturbation theory. Let us see how and in what new directions will be exposed to this variational principle, and we are just guided by our traditional textbooks, but I'm sure that This will expose us to a new horizon about the same approximate method. And I have a personal request to ma'am that she, if permits, schedule permits, she also motivate our student participants for facing these challenging topics. Some instance of her experience with students at University of Mumbai, she can share if she likes. So I'm giving it to ma'am. Ma'am, it's all yours now. And we are very privileged to get the guidance from you. And we will try to remain in touch with expert teams like you. Thank you, ma'am. Welcome you once again, and it's yours now.
Yeah, thank you, sir. So in this part of the morning lectures that I have been taking, I have just been talking about the basics of quantum mechanics. And I hope I have been able to cover the basics that you will need for understanding all these interesting subjects of quantum computation, information, cryptography, etc., which are being given a glimpse of in the afternoon lectures by experts. So today we continue our discussion. So what we have done so far is we have talked about the motivation for quantum mechanics in a historical manner. We have also talked about the formalism that is used. So we set up the formalism, and let me just present my screen. Yeah. Yeah. So we have set up the formalism. We have talked about the postulates. We have introduced the bracket notation. We have found the connection between the bracket notation. We have talked about the Schrodinger equation. And now today, what I'm going to do is, in the first lecture, give very simple examples of how you solve the Schrodinger equation in some very simple cases. And then I'll also talk about variational method as Dr. Singh mentioned. And in the second lecture, we'll talk about the Bell's inequality and hidden variable theories. So I start my lecture with a brief discussion of two-state systems. As you can see in quantum computation and quantum information theory, two-state systems are very useful. And here the advantage is that whatever concepts we have developed so far, with this very simple system in which the basis consists of only two states, it is two-dimensional basis, we can understand many of the concepts that we have developed. So let us consider a system which has only two states. It can be spin up and down states of an electron, or more practically, let it be an ammonia molecule in which the nitrogen is placed either above or below the plane, which is being formed by the three hydrogen atoms. So this is actually not a two-state system. In reality, it has multiple degrees of freedom. There are vibrational degrees of freedom, translational degrees of freedom, rotational degrees of freedom. What we are assuming here, it's a very simplified picture in which we are assuming that all the other degrees of freedom are frozen kind of thing. So there are no changes because of those effects. And the only perturbation that is present is because of this this degree of freedom, which is the spin. So we are assuming that the Hilbert space of our system is spanned by two basis states. I emphasize it is the simplification. And these two basis states I am going to call as plus and minus as before, and they are supposed to be orthonormal, which let me remind you means that they are orthogonal to each other. Both of them are normalized to 1, and then there is a completeness relation gives you the identity operator. And let us consider a Hermitian operator A in this space, which is associated with an observable A. So as we saw, each operator in the Hilbert space can be represented by a matrix once I choose a basis. So in this space, the basis is two-dimensional, and therefore the matrix representing the operator is also two-dimensional. The matrix elements are basically A11, A12, etc., which are obtained by putting the operator between the ket I and bra I and ket j, and so on. So if I express the operators as matrices, then I can also express the states as two-component spinors, which are called Pauli spinors. So when I write so all these notations can be used interchangeably. You can express the spin up state as plus or 1 or 1 0, and spin up down state as 2 or minus or 0 1. So given this basis, I can express any 2x2 Hermitian matrix as a linear combination of the 3 Pauli matrices and the 2x2 identity matrix. So this is a simple exercise which you can do. Just substitute for the Pauli matrices, which we wrote down yesterday, and express the matrix as express the operator in this form. So let us now quickly recall the time development of the system and apply it to this two-state system. So the time development of a state is given by the time evolution operator, which we introduced yesterday. This operator U acts on the initial state psi t and evolves it to a later time t plus dt. For infinitesimal time translations, it is given by 1 minus it over h cross times the Hamiltonian. And I can write so since the state is evolving with time, I can write the amplitude that at a certain time t, it will be in one of the eigenstates I, okay, which are your plus or minus, the basis states. So these CITs are the coefficients in the expansion of psi t over the basis state. Once I have the base state, I can express the ket representing the state as a superposition of the basis states. And since the state is evolving with time, the coefficients are also going to be time dependent. So CIT is the amplitude for the system to be in the base state I at a later time t. Now I want to find amplitude that the system which is in base I, in the basis state I, what is the amplitude probability that the system will be in state I after the system has evolved to time t plus dt. And that will again, just like the previous expression, it will be expressed by the inner product of I with the ket corresponding to the state at time t plus dt. Now in this last expression, I can substitute psi t plus dt by using the time evolution operator, and I get the matrix element of ut plus dt, t, the time evolution operator between the base state and the initial state psi t. What I have done now is I have inserted an identity operator. Remember the completeness relation, sum over j is the completeness, is the identity operator which I have inserted between u and psi t. Okay, we wrote something like this yesterday also. I hope it's clear what we are doing. The same expression, we are inserting an identity operator so that it becomes a product of j psi t, which is the amplitude for the initial state to be in the base state j, and the matrix element of the time evolution operator between initial and between I and j base states. And we call this, so this is basically the matrix element of u in the ijk basis, I basis. And for infinitesimal transformation, we have seen that it is given by this operator, which is on the top here. This is for the infinitesimal unitary transformation. If I take the matrix element of this object between I and j, the first term gives me a delta ij, and the second term gives me the minus it over h cross times the matrix element of H between I and J. There should be an I here. Okay. Okay. So that is the U matrix, which tells me how the system will evolve under an infinitesimal time evolution operator. So this gives me a relation between the coefficients in the expansion at time t and time t plus dt. You can see that the coefficient at time t plus dt depends on all the coefficients C1, T, C2, T, C and T, etc. at the initial time. So even if you start with the pure state, you can end up with a superposition of all the base states and vice versa. So this expression you can very easily show gives a differential equation for CIT. That is, you take the CJT part, the first term on the right hand side to the left, you will get the difference of Ci at time t plus dt and time t, divide by dt, and you will get minus I over h cross hij. And when you integrate over this equation, you can write this. So the left hand side you can write, when you take the limit dt going to 0, you get the time derivative of CIT. So this is the equation which gives me time evolution of the coefficients in the expansion of psi. Hij is called the Hamiltonian matrix, and it has to be Hermitian. Okay. Why? Because if it is not Hermitian, I will not be able to conserve probability. So mod CIT square is the probability that the system is in state I. If I sum over all of them, I should get 1. And this number 1 should be the same. Sum should be the same on both sides, whether at time t or time t plus dt. And you can show very easily that this will happen only if Hij is a Hermitian matrix. So for the two-state system, now let me write this differential equation for the two-state system. The two-state system, I goes from 1 to 2. So I have two differential equations, one for C1 and other for C2. Okay. And the right hand side, you have a linear combination of C1 and C2 in both of them. And you can check that the coefficients are H11, H12, H21, H22. You can see that this set of linear equations, as usual, can be written as a matrix equation. So at some time, if the state is represented by the ket psi, I can express psi as a linear combination of 1 and 2, which are actually your plus and minus. Remember, we mentioned yesterday, 1, 1 and 2, 2 are projection operators which project out the first component and second component, that is spin up component and spin down component. So these C1 and C2 are these coefficients, these inner products, 1 psi and 2 psi. So if the system is in some state at some instant t, then in general it may not be in the same state at a later time. And to find a position, to find the probability of it being in a different state, in the second state at a later time, we need to solve these equations. Okay, same equation that I wrote earlier. And so if I want to find the probability that the system will be in state 1, which started with a state 1, is in state 1 at a later time, I have to find the coefficient, all these coefficients, and put them in the expression for psi t. So we need to know the coefficients Hij's in order to be able to solve this equation. Okay. So Hij's are the matrix elements of H between I and J. Okay. So basically, you have to find the potential, and Vij will give you the probability that a system which was in state J initially, after the interaction has moved to state I. So we are dealing with the simplest case of two-state system like ammonia molecule. And in the simplest case, what will happen is that there is no possibility of a system which is in state 1 to be able to move to system 2, to state 2. Okay. So that is the simplest possibility. But there is no interaction which can cause, in case of ammonia molecule, which can cause the nitrogen to go from the upper side to lower side or vice versa. And in that case, these H12s, which are coupling state 2 and state 1, or state 1 and state 2, they will be 0. And the matrix will be, H matrix will be diagonal. And C1 and C2, differential equations for C1 and C2 will decouple. Okay. So these are the equations after decoupling when I put H12 and H210. And the solutions also simple, exponential solutions, oscillatory solutions with some constants. So in this case, if the system is in state 1 to begin with, it will remain in that state. If it is in system 2, it will remain in that state. And these are the amplitudes for the stationary states. So the states have definite energy. And because of symmetry of the problem, I can assume that these energies, H11 and H22 are also equal. And the state, let me call this E0, which is the ground state. However, there is some possibility that I give a little push to the nitrogen, and because of which it somehow crosses the potential barrier and some kind of quantum tunneling takes place, and it moves up to the other position, other side of the plane, which is containing the 3 hydrogen atoms. So it can move from plus to minus or minus to plus. There is a small probability for that the system will start in state 1 and then get to state 2. And by solving those differential equations, in case when H12 and H2 are not 0, I can calculate this probability. So again, I can take these coefficients to be equal because of the symmetry of the problem. There's no reason to believe that coupling of 1 to 2 will be different from coupling of 2 to 1. Let me call this, let me give it a name minus A. So my equations now become coupled differential equations with coefficients E0 A and E0 minus A and minus A E0. We can write it in the matrix form. Or you can just solve it by using the standard techniques, add and subtract. When I add and subtract, I get decoupled equations for C1 plus C2 and C1 minus C2, which as before will have the solutions, exponential solutions. And then I add and subtract them. I get the general solutions for C1 and C2 with 2 constants A and B, multiplying the minus I T over H cross term and minus plus I T over H cross term. So there is some mistake. There's some sign mistakes which I'll correct. So these signs must be, these signs are okay, fine. Okay, so what I have found is that C1 and C2, they have they are linear both combination of 2 plane waves with different frequencies. Frequencies are E0 minus A over H cross and E0 plus A over H cross. Okay. So if I put D equal to 0, then both will have the frequency, both C1 and C2 will have the frequency E0 minus A by H cross. Okay, and these will be stationary state. They will continue to remain in the same energy state. Similarly, there is another state with definite frequency, which is E0 plus A over H cross. So the level E0 has been split into 2 levels, E0 minus A and E0 plus A. There are 2 energy levels possible. Now there is some chance that the nitrogen atom can flip from one position upper to lower or lower to upper. And then in that case, what happens? Okay. So how does the system evolve? Okay, that is the question that I am asking now. So let me suppose that initially your molecule is in the state 1, which suppose state 1 is when the nitrogen is above the plane of hydrogen. What is the probability that the molecule will be found in state 2 at a later time? And what is the probability that it will be found to be in state 1 at a later time t? So these are given by these coefficients, and initial value of C1 and C2 will fix the constants A and B there. Okay, So initially the system is in state 1, which means C2 at time t equal to 0 is 0. In those equations that I had for C1t and C2t, here, if I put in these two equations, if I put time t equal to 0, I'll get C1 is equal to a plus b by 2 and C2 equal to a minus b by 2. So that is what I'm using there. I put C1 0 to be a plus b by 2 and C2 0 to be, so C1 0 to be 1 and C2 0 to be 0, which gives me equations for a plus b and a minus b, and you can simply solve and get a and b equal to 1. So the solution, using the initial conditions, I fix the constants a and b, and I get the solutions as these equations. Okay. So this, you can see that the bracketed quantities give me cos at and sin at kind of dependence, and therefore when I calculate the amplitude square, I will get C1t square, mod C1t square, varying as sin square at by over at over h cross, and C1t and C2t square will be sin square at by h cross. So initially C2t was 0, but now at a later time it is non-zero, and it is oscillating like the sin square of an angle. So if I plot C1 mod C1 square and mod C2 square, you will see this kind of curves. Okay, so the solid curve is for mod C1t square and the dashed curve is for mod C2t square. So initially the system is, what does it say? It says that the probability to be in either of the states oscillates between 0 and 1. To begin with, probability is 1 for the first state, the solid curve. So mod C1 t square is 1 at time t equal to 0. And then as time progresses, it starts coming down, decreasing, and C2t, which was initially 0, starts increasing, and both of them oscillate. And this is the kind of thing that Dr. Dey was talking the other day when somebody asked about the applications. Neutrino oscillations you have a similar phenomena, that you start with one kind of neutrino beam, and then as the system evolves, the electron type of neutrino beam gets converted into muon type, and vice versa. So that the total probability remains the same at any time. So the probability for being in state 1 also oscillates as cos square omega t was cross and omega t, and the other as sin square omega t, and omega 1 and omega t are the two frequencies when they are oscillating in phase or in opposite phase. So the system is in one or the other state initially. If you pull the nitrogen to one side, then you get a superposition of these two frequencies. If the system is not in one or the other of the definite frequency, and the splitting of the energy level occurs, which is a purely quantum mechanical effect, as we have just seen. And just a side remark that the Hamiltonian in this case can be written as a matrix, and the states can be written as Pauli spinors. And the matrix here is E naught minus A minus A E naught. It is a very, very simplified picture, and you can do more complicated things with it. You can put the magnetic field as the perturbation and do the calculations. But this was just an example of a simple finite quantum mechanical system which can be solved just by using the basic concepts of quantum mechanics. Now, there are many problems in quantum mechanics which cannot be solved exactly like what we did just now. And for those problems, we use variational methods. You can use variational methods for exactly solvable problems also. So there are, in general, there are different methods for finding approximate solution if the exact solution is not possible. So first is, of course, perturbation theory, which is done in your MSc course, and it is useful when you can write the Hamiltonian as a exactly solvable part and a small perturbation. We are not going to do all these here because of the time limitation. Semi-classical approximations are used when you have a slowly varying potential. And the third is variational method, which we are going to discuss now. So variational method is used when it is not possible to, when you have a complex system and we do not know how to diagonalize the Hamiltonian exactly. What do I mean by saying diagonalize the Hamiltonian? So if you have a time dependent Hamiltonian of a physical system, so you can write the Schrodinger equation. Basically, you can write the Schrodinger equation as a matrix equation for a finite system. And you can then solve this matrix equation and get the solution. So it is not always possible to do it analytically, and one has to take resort to approximation methods, and one of these methods is variational method. So what is the variational method? It is based on a certain inequality, which says that the mean value of the Hamiltonian or energy in an arbitrary state psi satisfies this inequality. That is, the expectation value of H divided by the normalization is always greater than equal to the ground state energy. Okay, so this quantity on the left is the mean value of the energy, and so if you make any measurement on a system, you will going to get a energy a value which is more than E naught, and this gives you a bound on the value of E naught. So E naught is the smallest eigenvalue of H or the ground state energy, and the inequality will become equality when if the state psi is a eigenvector of H with the eigenvalue E naught itself. You can apply this also to the other states apart from the ground state. The proof is very, very simple, and you should be able to follow it if you have followed the previous lectures. So I expand my ket vector psi on a set of basis vectors phi n, and then I calculate the numerator of the inequality, that is psi h psi. Okay. So now this matrix element is, how do you calculate it? You apply h to this psi, and this is going to give me En phi n. Okay, I substitute the linear expansion in both the ket and bra, and so I'll have double summation, which will double summation that is sum over n and sum over m, and the bra will give me Cn star phi m, and the ket will give me Cn phi n, and then H will act on phi n, and it will give me En, and what I will be left with will be Cm star Cn delta Mn. So that gives me my mod Cmn square. So the expectation value is mod Cn square En, which we did this also for particle in a box yesterday. And since En is greater than E naught, because E naught is the ground state energy, therefore I can write an inequality which says that this quantity is greater than E naught mod Cn square. But remember, what is mod Cn square? It is just the norm of psi. So I take it on the left hand side, mod Cn square, and I get the inequality which was there in equation 1. That is this equation. Okay, so this is mod Cn square, and the quantity on the numerator is mod Cn square En. Okay. So now to prove the inequality, we have proved the inequality, and now we want to use it to solve some problems. So this proof that we have constructed assumes that the energies are non-degenerate and the spectrum is discrete. I just mentioned that there are situations in which the spectrum may not be degenerate, and the states and the energies spectrum may be continuous also, and there may be degeneracy. There is a proof which exists for those cases also. We are not doing that here. So my variational method is based on this inequality. What does it do? It determines the ground state energy approximately because it is giving a bound. What you do in the method is you choose a family of state vectors which are parameterized by some parameter alpha. Okay, so alpha is some unknown parameter, and we choose a family of such gates. We call them the trial gates, and then we calculate the mean value of energy, that is H alpha, as a function of alpha. Because if psi depends on alpha, then mean value of H is also going to depend on alpha. Treat it as a function of alpha and minimize it, which means that you take the derivative with respect to alpha and put it equal to 0. You'll get an equation in alpha, and you find that you solve that equation, you get the minimum value, you get the value which will make the function, that is the mean value, E minimum. Okay. So the minimum value is obtained by minimizing, and this is an approximate minimizing, and it gives me an approximation to the ground state energy E naught. So let us do it for simplest case, that is harmonic oscillator. So this is a problem which you must have solved using the operator methods or by solving Schrodinger equation. And let us use this as a test case for solving this problem. So we consider the Hamiltonian of a harmonic oscillator. The standard thing, the first term is the kinetic energy term and the second is the potential energy. And we want to solve this by using the variational method. So what do I need? I need a trial function. So although you can use any trial function, most of the time you use some intuitive ideas to fix the trial function. For example, this is this potential is even in X. So I would like to try a trial function which is also even. So let me consider a one parameter family of functions, say exponential minus alpha x square. Okay, so this is the trial function. Alpha is a free parameter, which is greater than 0. So using this trial function, I calculate the left-hand side of the inequality in variational method. So this gives me psi alpha. Psi alpha is the inner product of the norm of this wave function, and in the position space, you know that it is calculated by calculating the quantity psi star psi dx. Okay. So psi star psi, because alpha is real, alpha x square is real, it just gives me integral of minus twice alpha x square, which I call I. You see that we don't need to calculate this, but if it can be calculated. Then I calculate the numerator of the inequality, which is the expectation value of H in this state psi alpha, where alpha is still unknown. So I substitute this Hamiltonian. I substitute for psi alpha star and psi alpha, and I evaluate this. So again, I'm not doing the full calculation, but you can verify that the second derivative of exponential minus alpha x square is going to give me something like h cross square over twice over alpha, and I get an equation like this. So this integral that is left is again I, and that is why I did not evaluate it. I can just take the ratio of this expectation value of H alpha with the norm of the vector. Okay. So now I find the value of alpha which will minimize this quantity, which is a function of alpha. And it turns out that the value for which the derivative of the mean value is 0 is alpha naught is equal to half m omega over h cross, and it gives me the ground state energy, which is half h cross omega, which is actually the exact energy. So in this case, I have been able to find the ground state which actually matches with the actual ground state, which you can find by other methods or by experiment. I can use the method again. Okay. So so this is the statement that in this case, the minimum value is exactly equal to the energy because I had chosen a trial function, which is actually the ground state wave function. So that is why I'm getting an exact solution. I can also calculate the first excited state in the same way. So the trial wave function for calculating E1 is going to be orthogonal to the wave function of the ground state. So therefore, I do the function like x exponential minus I alpha x square. I do the same exercise and I calculate the expectation value of h, calculate the norm of psi, take the ratio, and you get this function of alpha thrice h cross square over 2m alpha plus 3 by 8 m omega square over 1 alpha. And you take the derivative of that, put it that equal to 0, and you find that the quantity comes out to be 3 half h cross omega, which again is exact result. If you want to do a little experiment, you want to play around with the method, what you should do is to take some trial function which is not the actual wave function. So we can try other kind of trial functions. For example, you can try a wave function of the kind psi ax. This should be ax because a is the parameter. Instead of alpha, I am writing a as the parameter. So this psi ax is equal to 1 over x square plus a is a one parameter family of functions. As you change a, you get different functions. And you use this psi ax in the expectation value of h, calculate your wave functions, calculate your quantities, which is the expectation value of h and the norm, and take the ratio. And this time, please verify that you will end up with the value h cross omega over root 2, which is not the exact value. Okay, it is more than root 2 times more than the actual value. So this variational method actually gives you only a lower bound, and if you choose your trial function smartly, the lower bound can be that the value that you get will be very close to the actual value. You can solve other kind of problems also. For example, this Hamiltonian example 3 is the Hamiltonian for enharmonic oscillator, where you have a lambda x4 kind of potential. And you can try again a function of the kind minus ax square, say by 2, alpha x square by 2, and go through the same procedure. You can see that the difference will come from the previous case because of the change in the form of the potential. So you can minimize, and what you find is that the energy will be minimum for this value. So please do this. Okay, and show that the value it is minimum at the given value. And the last thing that I do is now give you another problem for electron in a Coulomb potential. Again, there are other methods to solve this problem. We are trying to do it using the variational method. So you take the ground state wave function. You want to calculate, so you make some guesses. For example, because of spherical symmetry, there will be no angular momentum. So your wave function, the trial wave function that you use, need not depend on theta and phi. It need not have any nodes, and it should have the property that as r goes to 0, it should become a constant, and as r goes to infinity, it should be 0. Sorry, it should be 0 as r goes to infinity. So this goes to at the boundary, it should approach 0. So if I try a function of the kind exponential minus alpha r square and put it and use the Hamiltonian in the spherical polar coordinates. So I need only the radial part of the Hamiltonian because I have chosen the wave function to be independent of theta and phi, and I can treat it as a one-dimensional problem. And so you can put this h between the So you can calculate psi star h psi dr and divided by the norm, and you will end up with the value of alpha, which is given here. And then when you put it in the expression for E, you find you'll get a result which is slightly above the true energy. Okay. So this is all we are going to do about variational method. I'll now switch to the next lecture. If there are any questions, we can take them now. Because now I want to talk about the hidden variables and Bell's inequality, which will take a longer time. We'll take a 2-minute pause, and if there are any questions, please ask. So can I start the next topic, if you allow?
Yeah, ma'am. You can proceed.
Because you have already given the introduction, so I guess okay, there's a question.
Chat box will take.
Ma'am, there's one query by Shailendra Singh, our UG student. Why we always find the ground state energy by trial method? Why not the other excited states?
You can do that. So I just now showed you that you can calculate even also. We did that for harmonic oscillator.
Yeah, sure. Because as excited state also we have taken also in the harmonic case, and then we can start also with the.
But the expression that the inequality that I have derived was for the ground state.
Yeah.
Not there. Yeah, because all the when you write sum over En mod Cn square, each of the En is greater than E naught, and from there that bound on E naught comes. But once you have found the E naught, once you have found the ground state energy and the wave function, corresponding wave function, then you can look for an orthogonal wave function and again use the procedure. Okay. So let me now start with the last topic, about which there have been a lot of discussion in these lectures, which is about the entanglement and things. So, so in the next 1.5 hours or so, I'm going to talk about the hidden variable theories and what is called the Bell's inequality. So this is this discussion about hidden variable theory started with the problems that Einstein was having with the interpretation of quantum mechanics. So let us just go over the basic ideas in quantum mechanics very quickly. The basic idea is that the measurement disturbs the system. As soon as you make, so in general, the system may be in a complicated state, which is a linear combination of different basis states. And as soon as you make the measurement, you disturb the system. And after the measurement, the system comes to a particular eigenstate, which is the eigenstate corresponding to the eigenvalue that you have measured. So the result of measurement always gives you the eigenvalue of the observable operator corresponding to the quantity that you are measuring. And after the measurement, the system jumps to the eigenstate of the operator corresponding to your observable. So now you consider a measurement which is being performed on a spin half system. which is in a state Z, and Z is an eigenstate of the operator Sz. So remember, yesterday we talked about spin, which has three components, say Sx, Sy, and Sz. And for a spin-R system, Sz can take two values, h cross by 2 or minus h cross by 2, which is the spin angular momentum. And Z here is the eigenstate of Sz with the eigenvalue h cross by 2. So if I make the measurement to find the spin along the x-axis, then the operator that I have to use will be Sx, and then the system will collapse either into state x or in state minus x. So x is the state in which the spin is pointing along the plus x direction, and minus x is the state in which the spin is pointing along the minus x direction, and they are eigenstates of the operator Sx. Okay? So Sx, x is h cross by 2x, Sx minus x is minus h cross by 2 minus x. And if the system is initially in the state Z, so you make measurement of the Z component of spin, as a result of which it comes to one of the eigenstates. Say it comes to the spin up state, which is here written as Z. Now in this, now I make a measurement on of the spin x spin component in the x direction. I can get either h cross by 2 or minus h cross by 2, because the state Z on which I am making the measurement now can be written as a linear combination of x and minus x with the same coefficient, and therefore the probability for either value occurring is half. So measurement has disturbed the system. We did this in Stern-Galak thought experiment also, that the measurement disturbs the system, and it only tells us the value of the measured observable after the measurement has been made. So it does not tell us anything about what was the value of the observable before the measurement. Okay, we have no information about what was the state of the system before I make the measurement, and after I make the measurement, I disturb the system. So I can only tell what is the state after the measurement. So I have no way to tell the value of the observable before the measurement was made. So the result obtained by a single measurement is not predictable. This also we discussed yesterday. That I cannot, the question, if I ask the question, what will be the value of the observable if I make a measurement, I can't tell that. In quantum mechanics, I can only tell the probability that this value will be measured. This is the probability that this value will be measured. What else you can predict is the statistical distribution of the results obtained if I make a number of experiments on same measurements on the identical system, which is the expectation value. So I prepare identical experiments, the replicas of my original experiment, and on each of them I measure the value of the observable. For an individual apparatus, I cannot tell what is going to be the value, but after I perform the measurement on all these replica experiments, then I can tell what is going to be the average value or the mean. So this fact that I have no information about what was the state before the measurement was made, Einstein was not comfortable with it. So these people, Einstein, Podolsky, and Rosen, they came up with this idea that there is something incomplete about what quantum mechanics is telling us. So they said that just because quantum mechanics does not tell us what was the state before the measurement was made, or that does not mean that the system was not in any state before the measurement was made. Or if the quantum mechanics tells us that we cannot make simultaneous measurement of certain variables, like an x and p, like Sx and Sy, that does not mean that their values did not exist before the measurement was made. Okay. So there are two things. One is whether the value existed and I did not know it, or whether the value was not fixed at all. Whether it was a superposition or it was in some state, it is just that when I make the measurement, I disturb it and I measure, I get certain value. Okay. So their argument goes as follows. So I'll try to explain the EPR argument, and then we'll see what how Bell came up with the certain inequalities to explain this fact, to resolve this paradox. So suppose I have two systems, 1 and 2, which interact during the time 0 to t. It is like the singlet of two spin states that people have been talking about. So there's a system 1 and 2 are coupled, connected to each other, and then they separate and they move far apart from each other. Okay, and they stop interacting. So if I write a combined wave function of the two, I can write it in this form. What is this form? I have a plane wave corresponding to particle 1 because they have moved apart, and I have a plane wave corresponding to particle 2. They are moving in opposite direction, so their momenta are opposite. So I add both of these plane wave solutions, I get this kind of exponential, which is delta x1 minus x2 plus x0. Okay, which means there is a distance between x1 and x2 equal to x0. So the thing that I wrote earlier is nothing but a product of two plane waves, okay, up x1 and u minus p x2. So this fact that the momentum is opposite in the two is related to the fact that they were originating from the same system. Okay, so it was at rest. They were at the same position, and then they moved in opposite direction with momentum p. So their momenta are always going to be equal and opposite, and that is why you have this up at x1 and u minus p x2 as the plane wave solutions for particle 1 and 2. So up x1 is the eigenstate of momentum with momentum p, and u minus p x2 is the eigenstate of momentum with eigenvalue minus p. X1 and x2 denote the position of x1 and x2 minus x0 denote the position of the particles 1 and 2. So if I make a measurement of momentum on system 1, I'm going to get one of the eigenvalues, and it is wave particle, so any momentum value is possible. So suppose I make the momentum and it comes out to be P naught. Once I make a measurement of the momentum of 1, it will come to the eigenstate corresponding to the momentum P that I have measured. So its state will become u P naught x1. Okay, and correspondingly, the momentum of second particle will also get fixed to minus P naught. So the value of the momentum of the system 2 will now become minus P naught. So once the measurement on system 1 yields the value P naught, the wave function will collapse to the state u P naught x1 psi minus P naught x2, which I can write in another form in the coordinate space, in terms of coordinate space wave functions, which are just delta x minus x1 and delta x minus x2 plus x minus x2 plus x0. So you can substitute these delta functions in this equation, and you will find that you will get a delta function which was there in the when I use the momentum representation on the earlier slide. Okay, here. This delta x1 minus x2 plus x0 I get from here also by using the coordinate space wave function, which are the delta functions. So for a particle at a fixed position, the coordinate space wave function is the delta function. So these are eigenfunctions of position. So if a measurement of position is performed on system 1 and I found the value to be capital X, then this delta function tells me that the wave function will collapse in such a way that the wave function of second system will become an eigenstate of the position with the value x minus x2, x plus x naught. Okay? So x2 will be x plus x naught or x1 plus x naught. Which means that I'm measuring they have moved far apart. I'm measuring the position of system 1 at some point, but that measurement is telling me the position of the system 2 at a faraway point. They are separated in space. Still, I can tell the position of the second particle if I measure the position of the first particle. So what Einstein, Brodsky, and Rosen said was that the system 1 should not have any influence on the system 2. Okay? How can I have something happening here affect something happening at a faraway point? So there should not the measurement of the reason I am able to find the value of system 2, position of or momentum of system 2 by measuring the momentum of system 1 is because the values were already there. Okay, they said instead of saying that the system was in a superposition of all possible eigenstates, until you make the measurement, you don't know where the particle is or what is the momentum of the particle. If you go by that, you can measure the momentum of system 1, but for this kind of states which are coupled, measurement on system 1 is also going to give me the value of the quantity for system 2, which is not possible. Okay? And therefore, there must be some other variables which contain the information that the system 2 has this position x0 plus x1. Okay? In other words, they said that the wave function that I am talking about in quantum mechanics does not contain all the information. There is some other information which is contained in some other variables which are hidden from us. These are called hidden variable theories. So we don't know. We are saying that we don't know what is the value of the position or momentum before the measurement is made because we don't have access to the hidden variables. So the values do exist even before the measurement is made. I am able to find the value only after I make the measurement, but they do exist earlier also, and they depend on the hidden variables also. Let me give another statement given by Bohm of the same with another example. To talk of, and this is the example that everybody has been talking about in their lectures. I have a system of two spin halves, A and B, which are in zero angular momentum state psi. Okay. So if I have two spin halves, they can add up, and when the spins they add vectorially, the total spin can be either 0 or 1. Okay. We have not done angular momentum theory, but we can discuss it if there is time left, how you add the angular momentum. So the total spin of two spin halves can be either 0 or 1. You can consider it by just enumerating all the SZ components. So if a spin is half, then SZ component can be half or minus half. If I have two spin halves, then total SZ can be 1, 0 or minus 1. So when SZ, that is SZ total is 1, then angular momentum also should be equal to 1 because SZ takes values from maximum value to minimum value. And then the fourth state will have SZ0 and S also 0. That is called a singlet state. So the two spin halves can combine to give either a spin 0 state or a spin 1 state. So we are talking about a combination in which the total spin is 0. So SA and SB, when they add, they give you value 0, and therefore each of the components of SA plus SB must also be 0. Which, if you write this vector equation into components, tells me that the ith component of SA must be opposite to the ith component of SB. In other words, if a particle spin spin of particle 1 is pointing upwards, and the spin of particle B must be pointing downwards. So I can be X, Y, or Z. So I start this state in which A and B are in a zero angular momentum state, and then A and B move apart. So total spin of the system is 0, and therefore their Z components must be pointing in opposite directions. And if I go by locality, then if I make, they are far apart, so measurement which I make on one of them should not affect the other one. Okay. However, because the total spin is 0, if I make a measurement on A, and I found it to be in spin up state, it automatically tells me that spin of B must be pointing downwards. So this is the expression psi AB that I have written in the bottom, is the wave function of this spin 0 system. Okay, two spin half combination in total angular momentum 0 state. So this cross is the direct product, and it shows it actually represents up down minus down up basically. So ZA is spin up, Z minus ZB is spin of B is down, and in the second term the spin of A is down and the spin of B is up. Okay, so I can write this as a antisymmetric combination of up down and down up. I could also express the state of the system by specifying the X component of spin instead of Z component. If I do that, I can write a similar expression in which the case XA and minus XB, etc. are eigenstates of the SX component of A or SX component of B. At a time, I can specify any one of the components of S along with S square. So S square and SZ form a complete set, which we discussed last time. I could also have taken S square and SX as the complete set. So, in this representation, I am expressing the state of the system AB in terms of the individual states, which are eigenstates of SX operator. So I could have done this also. And then if I make a measurement of SZ, then the measurement postulate tells me that the system will collapse to one of the two states. So SZ was, so before the measurement is made, the system is in this state, which is the singlet state, okay, scalar, spin 0 state. It can be either first spin is up, spin of A is up and spin of B is down, or spin of B is down and spin of A is up. It is an antisymmetric combination. There are some, this can be explained by in the theory of angular momentum. Before the measurement, this is the state of the system. Once I make the measurement, suppose I measure the spin of A, which has now moved far away from B, and I found it to be in spin up state. ZA is the spin up state. Quantum mechanics tells me that the act of measurement will bring the system down to the state corresponding to which I have found in the measurement. So initially it is a linear superposition of both the possibilities. For the combined system, there are two possibilities, up, down and down, up. There is equal probability for the system to be in either up, down or in down, up. Once I make the measurement and I find the spin of A to be up, the system will collapse to just this part. Okay. So I make a measurement on SAZ and it gives me a value h cross by 2, which means that the spin of A is in spin up configuration. So the measurement postulate tells me that the system, the wave function psi AB will now collapse to the first part of the wave function, which is ZA cross that minus ZB. But that tells me that the SZ component of B must be minus H cross by 2. So I made a measurement of A on A, and I have found the Z component of the spin of B. Okay. Now the measurement of A should not have influenced the value of B, and therefore this must have been present before the measurement. This is what they are saying. I could have also chosen to measure the X component of spin of B, and that will give me, so measurement of spin of B is going to give me the value of the X component of spin of B. So I make a measurement of B and find the value of X component of spin of B, and I make a measurement on A and I find the value of the Z component of spin of B. I'm measuring the spin of A, but because they are connected, spin of Z component of spin of A, determination of Z component of spin of A determines the Z component of spin of B also. So by making a measurement on A, I am able to find the Z component of spin of B, and by making a measurement of B, I am able to make find the X component of spin of B. But they cannot be measured simultaneously because they do not commute. Okay? So what this is telling me is that I can. So what they said was that Baum said was that according to this postulates of quantum mechanics, I can measure. I cannot measure two variables which do not commute simultaneously. But here, because of the connection of A and B, I am able to find both the X component and the Z component of B simultaneously. So this was the paradox. And to explain this paradox, they said there are some hidden variables. And these people suggested all kinds of hidden variable theories, which say that you construct a theory which has some other variables to which we don't have access. Okay? And these variables contain the information about the system, which is not accessible to us. And therefore, we say that we do not know what is the state of the system before the measurement is made. But the hidden variable has specified what is the value of the Z component, for example, even before the measurement is made. Okay. So the extra variable takes different values, and when several identical systems are prepared, then we call it identical because we do not have access to the hidden variable. However, each of these identically prepared systems that I have made for performing my experiment and finding the average values or probabilities, each one of them has a different value of the new hidden variable that I have introduced, to which I don't have access. So I don't have access to hidden variable. Therefore, I am saying that they are identical experiments. And therefore, I am saying that identical experiments are giving same result. Identical experiments can give different results. But for the person who has access to the hidden variable, they are not identical systems because the value of the hidden variable is different for all of them. Okay. And therefore, there is no uncertainty in the whole picture. It is not that quantum mechanics is wrong or the hidden variable theory is right. It is just that the quantum mechanics does not have full information. Because we don't have information about the hidden variable, therefore we talk in terms of probabilities. If I know the hidden variable, then there is no uncertainty. There is no question of probability. Each of the identically prepared experiments will be different. It will be the same in terms of all the variables that I am able to measure, but the hidden variable will be different for them. So these are the hidden variable theories. And if I can specify this extra variable, then it will fix all the different values of all the variables. Identical states prepared in replica experiments are not really identical. They differ in the values of the hidden variables. So how do I check this? if I integrate over the value of this hidden variable, hidden variable can has some parameter space, so it can take certain values. I do not have access to this, so what I am measuring is the average of all the experiments that are taking different value for hidden variable. So if I integrate over the hidden variable, I should get back my quantum mechanical result. Okay. So this is what we are going to discuss now, and then we will see how Bell came up with certain inequalities which are supposed to be satisfied if the hidden variable theories are local and they are consistent with quantum mechanics. And these inequalities were found to be violated by certain values of the parameters. So I think we can take a break at this point, and we can have questions now, or we can have questions after the discussion is over, as the students know.
Yeah, ma'am. I think it's a new topic, and seems to be, for me also, it's quite difficult, but still, in the next lecture, we can have the difficulties also discussed, and please repeat also some of the things in the next lecture, because it seems it's...
Okay, I'll start from the beginning again. If you wish, I'll start after 15 minutes. And I'm trying to go slow. I try to be very slow. And these are basically, there are more conceptual things here. And I will leave the calculation. I'll just give the, because there will be lots of calculations. I'll try to not get entangled in the calculation and try to convey the concept.
Yeah, thank you, ma'am. Thank you. So we'll be there at 11:30.
Yeah.
Shall we start, ma'am?
Yes, sir. I just want to ask the participants if this expression for the spin zero state that I wrote, is that clear, or should I explain that expression? ZB cross ZB minus ZB.
That is the last slide which you have shown, no? Regarding the spin states.
Yes,
Okay.
I'll show it. Just one second. I'm sharing the screen. Yeah. So this expression psi AB, are people comfortable with this, or should I just do it on the whiteboard for a minute? This expression.
Ma'am, I have just one query. Why it should be an antisymmetric wave function? Why not the
Right. Yeah, so that is what I was trying to figure out. So let us just go to the whiteboard for a minute, and I'll explain that. So we need to do a little bit of addition of angular momentum, basically, because this is important because everybody is using it. So that's why I thought I'll check. Okay. So what I'm going to discuss now is a brief diversion spin states of two electron system. Let us first remember, we talked about the spin space yesterday. For a spin half system, like electron, this space is two-dimensional. So it has a state plus and a state minus. This is the basis, which is also expressed as sometimes 1, 0 and 0, 1, the matrix representation, or as spin up and spin down. This is for a single electron. Okay. These states are eigenstates. What are these states? These states are eigenstates of the operators, complete set of commuting operators, which in this case is S square SZ. These are eigenstates of these operators with eigenvalues. Half plus 1 H cross square. This is the eigenvalue of the operator S square. And then there are also eigenstates of the operator SZ with eigenvalue MH cross, which in this case is plus or minus half. Okay, so these are your eigenvalue equations for this complete set of commuting operators which act in the two-dimensional space, which is called the spin space. This is for a single electron. Now I have two electrons. Okay, so I have a system A and a system B. Each one of them has a total spin of half. And I'm looking at the combined spin of the total system, which is SA plus SD. Okay, so I have to add two spin half, and this addition is done in the following way. S is a vector, so that has to be added vectorially. However, Sz is a scalar quantity. So when I add the two angular momenta, I have to make sure that the total spin of the combined system, Z component of that, is the sum of the Z components of spin of one first particle and spin of second particle. This is the thing that is used to get the total spin. So I had four configurations. Let us do it pictorially. I had spin up and spin down state of the first particle. I have spin up and spin down state of the second particle. And now I am looking at the spin states of the combined system. So what are the possibilities I can have? Both are spin up. First is spin up, second is spin down. First is spin down and second is spin up. And both are spin down. Okay. These are the 4 configurations in which the combined system can be. Now let us write the Z component of the spin of the total system, which is S1Z plus S2Z. So the first one, let us write the value of SZ for each of these configurations. So when both are spin up, then the total value of SZ is 1. Okay, because for spin up, the momentum is h cross by 2. For spin down, momentum is minus h cross by 2. So I'm just not adding h cross. I'm just writing the value of, multiple of h cross by 2. Yeah, I'm putting this h cross equal to 1 basically, which is what particle physics people do all the time. So the total value of SZ, so S1Z is half for spin up, and for spin down, S1Z is minus half. Ignoring the h cross, SZ for 1 plus 2 for this state is going to be 1. This state will be 0. This state will have SZ 0. And this state will have SZ minus 1. When SZ is plus 1 or minus 1, that means the total spin must be at least 1. Right? A spin 0 cannot have Z component equal to 1 or minus 1. So these two states must belong to S equal to 1. Now what are the spin states for S equal to 1? If S is 1, then M will be minus 1, 0 or 1. So the spin states of S equal to 1 are 1, 1, 1, 0 and 1, minus 1. Okay? 1, 1 is when SZ is 1. Therefore, this state must be up, up. 1 minus 1 is when SZ is minus 1. So this state has to be up, down, down. If I am writing in terms of the individual spins, the 1, 1 state of the combined system is up, up. And 1 minus 1 state of the combined system is down, down. Okay. Now I am left with these two. What about these? Both of them have SZ is equal to 0. So one of them must correspond to the 1, 0 state of spin 1. I still not identified that. It can be either up, down or down, up. Okay. Spin 1, total spin 1, total SZ 0 state can be either this or this, because both of them are satisfying SZ is equal to 0. However, they are forming a multiplet with these two. So I have 1, 1, 1 minus 1, and another state for in which the spins are opposite as the 1, 0 state. Now this state is symmetric under the interchange of particle A and B. This state is also symmetric under interchange of particle A and B. You can see from here. This is symmetric, this is symmetric. So this state must be the symmetric combination of up, down and down, up. Okay. So when two particles combine to give a spin, two spin-half particles combine to give a spin 0, then the 1, 0 state is the symmetric combination of up, down and down, up combination of the individual spins. Now I am left with the fourth state. Because to begin with, I had 4 combinations: up, 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 down, down, down. I have identified 3 of them: up, up, down, and symmetric combination of up, down, up. So what I am left with is the anti-symmetric combination of this, which has SZ is equal to 0. And it has no partner. It is the only particle left. It is the only state left. So therefore, it must have S equal to 0. So when two spin-half particles combine, they can give either S equal to 0 or S equal to 1. If their total Z component is 0, then they will be in spin 0 combination if they combine with if they for the antisymmetric combination, and they will belong to spin 1 if they combine in the symmetric combination. So that is the reason for that minus sign that occurs in the expansion of psi AB. Okay. So with that, I will now you can continue with the discussion that we were having. Okay. So is that clear? Yeah?
Yeah, it's clear, ma'am, now.
Yes. So now, so these are called a singlet and triplet combinations. Okay, so let me start from this example of bomb for the paradox. So the first way in which EPR formulated the puzzle was in terms of the position space and momentum space wave functions of two particles which were together to begin with, and then they separated. And now this is in the other example. I have two spin half particles A and B which are in the zero angular momentum state, which means SAI and SBI are equal and opposite, because if there are only two possibilities for SAZ plus SBZ, either it is 0 or 1. So if it is 1, then it cannot be in spin 0 configuration, total spin 0 configuration. Therefore, their Z components must be opposite, and the wave function is constructed in this way. So here this ZA that I have written is the spin up of particle A, minus Z ket is the spin down of particle B. Similarly, minus ZA is the spin down of particle A, and ZB is the spin up of the particle B. So psi AB is can also be written in terms of the eigenstates of the Sx operator. So these kets here, XA and minus XB, etc., are eigenkets of X component of spin of S, or X component of spin of A, or X component of spin of B. So again, you have the antisymmetric combination because the total Sx must be 0 for this state, which is a zero angular momentum state. So then I say that I make a measurement of SAZ, that is the two spin halves are separated, they are far away from each other. I make a measurement of the Z component of spin of A. We know that after measurement, it can be, before the measurement, it can be in any linear combination of plus and minus or up and down, but after I make the measurement, it will jump to either spin up or spin down, up and down or with respect to the Z axis. So I make the measurement and I find that it is in the up state, H cross by 2. So the measurement postulate says that once I make the measurement and find a value, the system will jump to the state corresponding to this eigenvalue. So my original wave function, original state vector had two terms. You can just replace XA and XB in the first line by Z and ZB. Everywhere you replace x, y, z, you'll get the equation that we had on the previous page. I have made the measurement and I find that ZA is 1. After the measurement, the system will, instead of being the superposition, it will jump to a state in which ZA is equal to 1, which means the second part is not possible. And the state vector will now be represented by only the first part of this expression, which is ZA cross Z minus ZB. But in this state, the spin of Z component of spin of B is also defined. It is not a combination of minus ZB and plus ZB anymore. So once I made a measurement of the Z component of the spin of A, I have automatically determined the Z component of the spin of B. In a sense, I am making a measurement here at some point, and at a faraway point, I am measuring something. So how do I know? So this was the problem that Einstein was having, that this is action at a distance. How does B know that A has been measured and it has found the value plus h cross by 2, and therefore I should have value minus h cross by 2. So since a measurement of A could not have influenced B, Einstein argued that it must be predetermined. The spin orientation must be predetermined. Just when we separate, the particles must already be having spin up and spin down configuration. It is not the quantum mechanical picture. Is till you make the measurement, they are in the superposition of spin up and spin down states, each one of them. Einstein says, no, they were already, and they were separated, already they had decided that A will be spin up and B will be spin down. And it is just that when I measure it, then I come to know that they are in spin up and spin down state. So it is a shortcut, it is a incompleteness of quantum mechanics that we don't know from the beginning that they were in spin up and spin down state. The hidden variable theory, if I had access to the hidden variables, then I would have now known from the beginning that they were in spin up and spin down state. So one picture is that they are in spin zero total state, and then they separate, and each one of them is in a superposition of both plus and minus. If I make the measurement, then this jumps to plus, and therefore this must be minus. Einstein's view is that they were already, when they started separating, they were already in up plus and minus states. It is only because and that is why when I measure A, I find up, and B is also minus B automatically because of angular momentum conservation. So, and then other thing about uncertainty principle is that if I measure the spin of A and I find that it is pointing upwards, then I have determined the Z component of spin of B. But I can also measure the X component of spin of B, and there I am measuring both spin of A and spin X and Z component of spin of B simultaneously, which is not allowed by quantum mechanics. So the hidden variable theories, which were proposed, Bell actually worked on that, so other people also worked on that. The idea was you should have a theory. So for Einstein and others, it was just an idea. It was a conceptual problem. Bell actually made it quantitative in terms of some by adding up inequalities as criteria for deciding whether hidden variables are there or not. So you construct a theory. Idea is that you construct a theory with hidden variables, and these hidden variables will take different values for different identical systems. So when I am saying that I am preparing a replica of experiment, of the same experiment, I am making measurement on a replica of the same experiment, and I am finding different values in each replica. Hidden variable theory will say that no, they are not identical. The person who has access to hidden variable theory will be able to distinguish between these replicas, and for them they are already different, and that different value of the hidden variable will decide what is going to be the outcome of your measurement. So it's like not knowing all the parameters of your theory. Because I don't know all the parameters, therefore I have this probabilistic interpretation that I say that the result will be one of these. But if I have this extra information given by the hidden variable, then from the beginning I'll be able to tell what is going to be the value. So if I can fix these hidden variables, this will fix the value of all the variables, and identical states which we are saying are prepared in the replica experiment will actually not be identical. They will have, each one of them will have a different value of the hidden variable. Now now we know that quantum mechanics we don't understand, but we know that it gives correct results. Okay, it matches with its prediction match with the experiment. Therefore, whatever is this hidden variable theory is, it should give the same results as quantum mechanics is doing. So it should be consistent with quantum mechanics. That is what Bell said. So suppose I have an observable A, which has eigenvalues A1, A2, etc., which I collectively call VA, and I have another observable which has eigenvalues V1, V2, etc., which are called VB. If A and B commute, then it is possible to construct states which are simultaneous eigenvectors of A and B, which we discussed yesterday. We'll see it in a minute. So this is the eigenvalue equation for A, and this is the eigenvalue equation for B. If they commute, and they have common set of eigenfunctions. Okay. So if you take the commutator of these two and apply it on phi, you will find that it is equal to 0. And you can do the thing in reverse order and say that the commuting operators have common eigenvectors. So suppose I have, I take A to be Sz. Okay. VA is the spectrum of eigenvalues of A. Therefore, VA can take values plus h cross by 2 or minus h cross by 2. So this is the way that John Bell constructed the hidden variable theory. Suppose I have, I take the spin half system in the in an eigenstate of the operator S3. Okay. So S3 was the Z component, which was h cross by 2 sigma Z. So each of the three components of yesterday we constructed these for Sx, Sy, and S plus S minus. As the S3 is even simpler because the spinors are just, it acts on plus and gives me plus, it acts on minus and gives me minus, minus of minus. So it is just the diagonal matrix 1 minus 1. This matrix has eigenvalues plus h cross by 2 and minus h cross by 2, and the corresponding eigenvectors are 1, 0, and 0, 1. So plus is the spin up ket corresponding to spin up state, and eigenvalue h cross by 2. Now I measure, I am calling it S3. Okay, instead of Sz, I am calling S3. So I measure, I make a measurement of Sz or S3. I find it the value to be h cross by 2. I know it is in the spin up state of the with respect to the z axis. And as a result of the measurement, the system will now jump to the state plus or 1, 0. On this state, I make a measurement of S1, which is the x component of spin. So the quantum mechanics says that this is Sx is going to be a linear combination of Sz is this 1, 0 is going to be a linear combination of eigenstates of Sx, which are again 2 in number. So Sx can take values plus h cross by 2 and minus h cross by 2, and it will be a linear combination of the two. The probability is 50% that I will measure it to be h plus h cross by 2, and probability is minus h cross is 50%, and I will measure it to be minus h cross by 2. Same way as we did in the Sternberg experiment. But unless I make the measurement, I do not know whether it will be h cross by 2 or minus h cross by 2. So hidden variable theory says that there is another variable which is going to tell me, which can tell me from the beginning whether it is going to be h cross by 2 or minus h cross by 2. Before making the measurement, I can tell whether the result will be h cross by 2 or minus h cross by 2 if I know the value of the hidden variable. So what should be the hidden variable in this case? That is what Bell did. So we construct an operator A. So in this space, in this two-dimensional space, the operators are 2 by 2 matrices, and any 2 by 2 matrix can be written as a linear combination of Pauli matrix and identity matrix. This expression we wrote yesterday also. So let me write this operator A, and let me consider a state, arbitrary state n hat. N hat can be x, y, or z axis or any arbitrary direction in the space. And let me call the eigenstate of this component of sigma along the direction of n. Let me call it n hat, just like we call z as the eigenstate of sz or sigma z. So n hat is the eigenstate of sigma dot n, and the other equation is the complex conjugate of that. Okay. Now I multiply this equation, each of these equations, by n hat on the left hand side. Okay. Okay. So what I have done in the second equation is, I am not okay. Just a minute. I'll just correct this. Okay, I'm calculating this quantity. Okay. Yeah. So sigma dot n, sigma I n. I can write this as sigma I, sigma dot n. These two are equal, and therefore I can write it as the average of the two. Okay. And this quantity so I'm calculating the object NAN, which if you substitute the expansion of A in terms of the Pauli matrices, gives me A naught plus n hat sigma I n. When I is being repeated, and that means I'm summing over all possible values of I. So this is A naught plus A dot n vector. Eigenvalues of this operator A are A naught plus minus A, which you can easily check. It was a simple 2 by 2 matrix. And if I make a measurement of A, it will return one of these eigenvalues. In the hidden variable theory, once the variable is fixed, the value of A will be fixed. In quantum mechanics, I say that once I make the measurement, the result of the measurement will be either A naught plus A or A naught minus A. If I'm measuring A, the possible outcome will be one of the eigenvalues. So all I can say is before making the measurement is that the result will be either A naught plus A or A naught minus A. But the hidden variable theory says that there is another variable which will tell me, which already fixes whether it is going to be A naught plus A or A naught minus A. So what Bell did was, he constructed a unit vector M, another unit vector M hat, which can take all possible values in all over the space. And it is chosen with the following property, that if I can, so now in the hidden variable theory, when I calculate the expectation value of A in the state n hat, I have to mention the hidden variable also. Okay, if I don't have that M hat in the equation here, if I don't write this M here and here, then I will be calculating n hat, A n hat, which is the expectation value of A in the state n as we know it in quantum mechanics. Hidden variable theory, the state has to be labeled by one more variable which I have chosen to be an arbitrary vector in the space called M. And in hidden variable theory, this M can take two different values, or rather M can take certain values, so that by looking at this M, I will be able to tell whether the outcome is going to be A naught plus A or A naught minus A. Again, let me repeat. In quantum mechanics, I am measuring A on the state n hat. The result of all I can say before making the measurement is that the result will be either A naught plus A or A naught minus A. When I make the measurement, the system will come to a particular state, and I will know the value of the eigenvalue of the operator A. That is after the measurement is made. The hidden variable theory, the state n has one more label, m, which I was not aware of, which we are not aware of. And this other variable already decides whether you are going to measure a naught plus a or a naught minus a. This is what Einstein said, that it is predetermined. The outcome is predetermined. It is not what we are saying in quantum mechanics is not possible. It's not physical to me. So how do I do that? I say that if the vector m plus n projection of the vector a along m plus n along a is positive, then the expectation value is going to be a naught plus a. If it is negative, then expectation value is going to be a naught minus a. What does that mean? Just take the example. If n hat is along the y-axis, then m has a positive component along the y-axis. So this m can be anywhere in the space. If it is along the in the plane to the right of the exact plane, if in the positive quadrant of on the positive side of y-axis, then I will measure a naught plus a. If it makes an angle with a which gives me negative dot product, then I am going to measure a naught minus a. And so these statements can be written in the form of this equation, where this theta function is the function which takes value 1 if the argument is positive, and it takes value 0 if the argument is negative. So if a dot m plus n is positive, then the expectation value is a naught plus a. If a dot m plus n is negative, then this becomes 0 and this becomes 1, and I get the value a naught minus a. Now this variable is hidden. It is not accessible to us, and therefore when we measure, we do not know what is the value of m, and therefore we say that it's slightly the result can be either a naught plus a or a naught minus a. But the person who has access to this hidden variable, he will be knowing the value of this observable that I have constructed a dot m plus n, and he will be, by looking at whether it is positive or negative, he will be able to tell whether I will measure a naught plus a or a naught minus a. However, the result that I get should be using quantum mechanics should be consistent with what the result, what the hidden variable theory is giving. So now if I calculate the expectation value in my space, where I have no access to m hat, it should match with the sum over all the probabilities, sum over average, sum over all the values that you measure in the hidden variable theory. In other words, if I integrate over all m hats, if I take the average over all the values of the expectation value in the hidden variable theory, I should get back the quantum mechanical result. Okay. So in the hidden variable theory, I have one extra variable, and therefore when I calculate the expectation value, it is between states which have one more symbol apart from the label that I have put in my theory and had. But since I do not have access to m, to match my results with the hidden variable theory result, I should sum over all the possible m values. So the integral over all the angles m hat should give me back the result of the quantum mechanics. Integrating over the hidden variable gives the quantum mechanical result. Okay. Okay. So this construction of hidden variable theory, and it actually in the example that we just discussed, the two-dimensional case, it works. So the hidden variable result integrated over all the angles does give the quantum mechanical result. So this construction of Bell of hidden variable theory was a two-dimensional example. It produced the quantum mechanical result. However, it was shown later by other people, Bell himself also probably, that these kind of theories do not exist in dimensions higher than 2. Okay, so these are the words various people. In fact, there is a nice example given by Mermin, which I am not able to do because of the time constraint, in which he showed that this hidden variable theories, this interpretation of hidden variable theories being the more general ones and integrating over the hidden variable, giving the quantum mechanical result does not hold if you are in theories higher than 2 dimensions. And therefore, in our world also, this interpretation is not valid. So these are so then Bell constructed certain inequalities between observables, and he showed that the quantum mechanical predictions violate these inequalities. So hidden variable theories predict certain inequalities. If they are obeyed by quantum mechanics, then my quantum mechanics is consistent with the hidden variable theory. However, he could construct examples where he showed that the quantum mechanical systems can violate these inequalities. And then later on, a number of experiments were also performed, which verified that the quantum mechanical predictions were correct. So these inequalities are called BCHSH inequalities, given after the name of the people who proposed them. So initially, Bell proposed an inequality using the spin-half system example, and later on, these other people, Clauser, Horn, Shimoni, and Holt, they gave examples from using a photons of similar examples, as we will discuss now for Bell's inequality. And they all showed that this idea that hidden variable theories are consistent with quantum mechanics is not correct. So this is what we are going to discuss now in the rest of the lecture. So Bell said that the hidden variable theories need to satisfy certain inequalities, and then he showed that these inequalities are not satisfied by certain states in quantum mechanics. So first we'll construct the inequalities, and then we'll show what kind of situations, what kind of states in quantum mechanics do not obey these inequalities. Several predictions were performed. So there are many such discussions by various people, and they were they were also have been verified experimentally. So in Bell's construction, we consider a composite system again of 2 spin-off particles as before, and this time the spins of A and B are pointing in directions n minus n or minus n and plus n. n and minus n are eigenstates of the operator sigma dot n with eigenvalues +1 and -1, and the total spin is written as SA cross IB plus I cross SB. So this is a direct product space. The space of the system AB is a direct product space. Direct product of the space of A and space of B. So when I am writing SA cross IB, this operator is going to act on, SA is acting on the state space of A. IB is going to act on the state space of B, and IB is the identity operator. And similarly, the second term is I does not do anything to the spin of 1, and B changes the spin of B. So this is the total spin of the AB system. Now this spin is 0, okay, because we have constructed our state combined state to be in spin 0 configuration. Which tells me that SA cross IB must be minus of my I cross SB. This is the relation which we will use. Now we consider this object, which is the expectation value of SA cross alpha hat, SA dot alpha hat cross IB times IA cross SB dot beta hat. So alpha hat and beta hat are some arbitrary directions in space, SA dot alpha hat is the component of SA in the alpha direction. SB dot beta is the component of SB in the beta direction. Psi is the state in which my system is. It is an arbitrary state. So then I can show by doing some algebra that this quantity, this expectation value comes out to be minus h cross by 2 by 4 alpha dot b. Okay. So I'm skipping the steps, but you can see that this state psi is a combination of up down and down up. On the first spin, the operators of SA are acting. On the second spin, the operators of SB are acting. And therefore, this product that is inside the expectation value is going to act on the spins and going to produce h cross or minus h cross by 2 or minus h cross by 2. And that is how you get this factor of h cross square by 4. And this alpha dot beta comes when I use some vector identities. Okay. So you take this from me that the expectation value of this particular object turns out to be minus h cross square by 4 alpha dot b. If there is enough time, if I finish early, I'll do these identities on the whiteboard. Because it's really difficult to do everything in the, explain everything in PowerPoint. So I consider a hidden variable theory. What is hidden variable theory? It will have additional variables. Okay, and these variables will specify the system completely as claimed by Einstein and others. Suppose I call this hidden variable to be mu. Okay, so there will be more than one hidden variable. Collectively, let me call them mu. And when I prepare several identical systems, which are identical to me, these identical systems will have different values of mu, hidden variable. Now I consider the observable as SA dot alpha hat, which is some component of SA in some arbitrary direction alpha. So just like Sx, Sy, and Sz, the effect of measurement will be to give eigenvalues plus h cross by 2 or minus h cross by 2. So I have an observable SA dot alpha hat, which has eigenvalues h cross by 2 or minus h cross by 2, which will be reproduced by the observation. I call this quantity O SA dot alpha mu. In my hidden variable theory, the observable will depend on not only the spin component but also on the hidden variable. Okay, and by fixing the value of mu, I can tell in hidden variable theory what will be the value of observable, whether it will be plus h cross by 2 or minus h cross by 2. Now, the measurement of SA dot alpha does not depend upon the outcome of the measurement of B, as which is far away. Okay, this is the requirement of locality which Einstein was insisting on. That the measurement of any measurement of A is not going to affect the measurement of B. So now I consider this correlation function with SA dot alpha hat and SB dot beta hat. And this should again match between the hidden variable theory and the quantum mechanical result if I integrate over all the possible values of the hidden variable. So this kappa mu is some weight and OSA dot alpha hat are the values measured in hidden variable theory. OSA dot alpha hat and OSB dot beta hat are values measured in the hidden variable theory. And SA dot alpha, SA dot beta are values measured in quantum mechanics. So in hidden variable theory, I integrate over all the possible values of the hidden variable. It will reproduce the quantum mechanical result if the correlation function calculated in quantum mechanics is the same as this integral. Okay. So the Bell inequality, the inequality that Bell showed was that if I take a third direction gamma and I calculate this quantity E alpha hat beta hat, which is given here in the integral, by the integral. This quantity for the directions alpha and beta, subtract from that the correlation when the angles are alpha and gamma, a third direction gamma, then the magnitude of this object should be less than or equal to the expression on the right hand side, which is h cross square by 4 plus E of beta gamma. What are alpha, beta, gamma? They are some directions in space. Unit vectors in some directions. So this is called the Bayes inequality for the singlet state. For this particular example, this is the inequality that Bell derived, which we will probably do because we have a lot of extra time. But what was found was that if you choose your states suitably, that is, if you choose the angle alpha, beta, and gamma in a particular fashion, this inequality is violated. And this is a very simple example. You take alpha and beta and gamma to be making angles of pi by 3 with one another. Alpha and beta pi by 3, beta and gamma pi by 3, and alpha and gamma is 2 pi by 3. And then you can calculate these quantities. You can substitute these quantities in this expression, and what you find is, so alpha dot gamma will be cosine of 2 pi by 3, which is minus half. Alpha dot gamma and alpha dot beta and beta dot gamma will be cosine of pi by 3, which is 1/2. Just substitute in this expression, and what you find is that the left hand side is h cross square by 4, and the right hand side is h cross square by 8, and the inequality is violated. Okay. So this was the thing that this was one of the inequalities which was shown to be violated. So so let me just first discuss what is the consequence of this, and then we'll go back to the whiteboard and do the algebra also. What is happening here is, so the idea is that Einstein is saying that there is a hidden variable, and in that theory, in the hidden variable theory, I do not have this uncertainty about what I do, that I don't know what is going to be the outcome of my result beforehand. In hidden variable theory, there is an extra variable which fixes the possible outcome. If there are two possible outcomes, A0 plus A and A0 minus A, the hidden variable has already, the value of hidden variable tells what is going to be the outcome. However, in quantum mechanics, I do not have access to the hidden variable. Therefore, I can only say that the value will be A0 plus A and A0 minus A. However, quantum mechanics matches with the experiment. So whatever result hidden variable theory is telling me should be consistent with the quantum mechanical result. How do I come from the hidden variable theory to the quantum mechanical result? By integrating over all the possible values of hidden variable, because I don't know that. Now, all the local hidden variable theories which were constructed, these inequalities are for those theories. So what the statement is that if I assume that the locality, if I construct a local hidden variable theory, then the predictions of that in terms of inequalities are not valid in quantum mechanics. So they contradict the quantum mechanical predictions, and therefore it is not possible to construct a local hidden variable theory which will give a better description of the world than what quantum mechanics does. So again, the point is not between quantum mechanics and hidden variable theory. He was never saying that quantum mechanics is wrong. He was just saying that quantum mechanics is incomplete. It does not have. It talks about in terms of probabilities because it does not have access to the full information. There are more variables which we don't know. However, starting with that assumption and assuming locality, we come up with contradictions, and therefore this feature is inherent in the system. What the quantum mechanical prediction that if I measure spin of A at Z, if I find spin of A at some point, spin of B is automatically decided. And yesterday we heard this talk where we heard about experiments having been performed to confirm these things. So now if you wish, I can go through the derivation also, or I can take questions. So shall we go, Singh sir, shall we go to derive these things? I would like to do it, yeah.
Ma'am, we still have sufficient amount of time, so we can go for the derivation also.
Right. So I'll go to the whiteboard then, and I'll just do the missing steps.
Yeah.
Because otherwise it doesn't really make sense. Okay. Okay. So what they are trying to do is to write a hidden variable theory and get some get the inequalities and then show that they are not consistent. Okay. So I have two spin-off particles in singular state, which are represented by this wave function. Okay. And these vectors are eigenkets of sigma dot n है. Its eigenvalue plus and minus 1. So I wrote the total spin operator as AB, which was SA cross IB plus IA cross SB. So the meaning of this cross product is that they are this is a direct product. So the first factor acts on the. So I have two spaces ES1 cross ES2. My spin space of the two particle system is ES1 cross ES2. I have two particles, so therefore the first operator acts in the first space and the second operator acts in the second space. So when I apply this as AB on the combined state, like up down or something like that, then the first term will change the spin of the first particle, second will not do anything to the second particle, and the second term will leave this invariant and it will change the spin of the second particle. Okay. So now I construct this object which I wrote AB psi SA dot alpha cross IB times IA cross SB dot beta This is the observable that I am trying to construct. This is what I want to calculate. So I had this identity for the spin zero particle, that is SA cross IB minus
Ma'am, your voice is not coming to us. You are not audible, ma'am. Ma'am, your voice is not coming. You are not audible. Ma'am, you are visible, but audio is not coming to us. There is some problem with the audio. No, ma'am, you are not audible.
If it does not work, please reconnect.
Sir, ma'am's audio is not coming clear. She is visible,
So,
but she is not coming clear. Even her that screen is not visible to us also. Maybe some multiple connections from her side.
Hello?
Yeah, ma'am, you are now audible and visible both.
Okay.
You are audible now,
okay.
ma'am. Yeah.
So, let me try to do this. What I was trying to do. So, I'll not be able to see the screen, but I'll be. So, you have to tell me if something is goes missing. Because earlier I was checking whether I'm connected or not. Now I can't do that. So, I have this observable. And I'm finding the value of expectation value in this state psi AB, which we had written earlier.
Excuse me, ma'am, nothing is visible to all of us. Nothing is visible. Only your audio and that too is not clear, ma'am. Nothing is visible.
Wait a minute.
There seems to be some internet issues from ma'am's side.
Dr. S.P. Singh,
Sir,
Anuradha ma'am has some problem with her laptop.
okay,
That's
ma'am.
what she told me on the phone. She is joining on laptop and then continue with the lecture.
Okay, okay, sir.
Can you hear me now?
Yeah, ma'am, now you are loud and clear, ma'am. You are audible, ma'am.
Okay, fine. So, okay, then I'm using two devices again. So let me see. Okay. So this is the state, a singlet state, and this is the observable. I'm trying to find the expectation value of this observable in this state. So we had this identity because SA plus SB, SA cross IB, sorry, so SA cross IB plus IB cross SB, IA cross SB, acting on this state gives me 0. So that gives me SA cross IB acting on psi AB is negative of IA minus IA cross SB acting on psi AB. Okay. So I use this and I replace this factor here by this. Okay. So I get AB psi SA dot alpha cross IB SA dot beta cross IB okay, and then I use this identity which is I was talking about A cross B dot C cross D can be written as A dot C cross B dot D. Now I use this and I can write, so identify these with the operators in here. So I'm going to get SA dot SB and alpha dot beta. So S dot alpha S dot beta. Remember the identity we had written for sigma I sigma j. Sigma dot A, sigma dot B. Is A dot B plus I sigma dot A cross B. Okay. So we use that and we write S dot alpha hat, S dot beta hat is equal to H cross square by 4, because S is H cross by 2 sigma for dot beta plus I by I H cross by 2. Cross product is epsilon I j k alpha I beta j, and then your S A cross I B cross S B, sorry, times I A. Now it turns out that this thing is 0 for something because of something called Wigner-Eckhart theorem, and finally what is left in here is just your minus H cross square by 4 alpha dot beta. So that is what I had in my expression for inequality. Okay. So I have these observables SA dot alpha hat and SB dot alpha hat dot beta hat, and in the hidden variable theory I will also have another variable mu. So this is the outcome of the measurement of SA dot alpha. And similarly for the other one, this thing. Okay. So I with these so in the hidden variable theory I also have this extra variable mu, and with these I construct this object which is the correlator alpha beta hidden variable theory, which is the integral over all the parameters of the hidden variable theory of these observables which are corresponding to SA dot alpha in my theory, with this extra index beta mu. Okay. So the statement was that hidden variable theory should reproduce the quantum mechanical result. Which means if this integrated thing should give me what I am expecting from quantum mechanics. Okay. So I can calculate these objects in quantum mechanics, and if I choose alpha to be equal to beta, then that gives me E alpha beta in quantum mechanics to be minus H cross square by 4. Dr. Singh, it will take a little more time, so what do I do? You are muted, sir. Singh, sir, you are muted. आपकी आवाज नहीं आ रही है.
Ma'am, you can continue because we have lost some time with that internet issue. So you can continue, no problem, ma'am. It's very interesting.
Okay. Otherwise, we can do it in that extra hour also, if you want to give a break for lunch.
No, ma'am. For another 5 minutes, we can continue, no problem.
Okay, let me see what I can do in 5 minutes.
Yes.
So, is the idea clear? That we have constructed an observable, we have calculated it in the hidden variable theory, and we want to we we want to show that it will be the same if we calculate it in quantum mechanics. So this observable that we have calculated, with that I'm going to write down the inequality. Let me write down the object E alpha hat beta hat minus E alpha hat gamma hat. So gamma hat is in some third direction. So in my put it back in the integral. This is the correlator. And the second expression will have gamma instead of beta. Okay. And now I construct the object E the magnitude of the difference of these two. Okay, and this magnitude, because of it is equal to this integral, is going to be less than equal to mu kappa mu and this quantity over here. So I'm not writing it again. It's the same thing as what I have in the previous equation, and I rewrite this again. These over all the possible values of mu. So I take out from this bracket, I take out this quantity. Then what is left is 1 minus O SB dot beta mu inverse, because it was not there in the second term. See, the second term is just this gamma and alpha, beta was not there, so I multiplied by S inverse. And I have O SB dot gamma. Now the first one is just H cross square by 2. This one. Each one of them has the value H cross by 2 minus H cross by 2. So the magnitude will have H cross square by 4. Okay. Similarly, so that I am using right O SB dot beta mu is H cross square by 4. So that gives me this quantity, that this bracketed quantity that I have constructed, to be less than or equal to mu kappa mu H cross square by 4 for the product. Okay. Mod of 1 minus 4 over square. So SB dot beta mu O SB dot gamma. And this is a positive quantity. So the inequality between here I am integrating. When I integrate 1 over all the values of mu, I'll just get 1. And the second one is an integral. It's mu kappa mu. And positive, so there was something else. O of another term multiplying this. It is O of SA mu dot S3 mu. Dot mu dot S3 dot gamma, which is E. The figure that is left here is, please find it out, E of beta dot gamma. Ultimately, I get this identity inequality, which is E alpha beta minus E alpha gamma. Mod of this difference is less than equal to h cross squared by 4 plus E of beta gamma. Now you can check it for the value that I already had in the PPT. So alpha dot beta is 2 pi by 3. Beta dot gamma is also 2 pi by 3. Sorry, pi by 3. And alpha dot gamma is 2 by 3. So that fixes the values of this coefficient, alpha dot beta. So you don't have to search for all the values. You have to just find one example, one value of the angle alpha beta gamma, which will violate the inequality. So this is minus h cross square by 4 times half, and the same is with E beta dot gamma, and E alpha dot gamma comes out to be h cross square by 8, and that finally gives me the inequality violated. So I have some values in the inequality is not obeyed by some states. I have constructed a state and an observable for which the inequality is not valid. So that was the indication that was Bell's proof that the hidden variable are not. So we can stop at this point. If there are any questions, I can take them now.
Ma'am, as such, I do not see any question in the chat box.
I realized it was a little heavy for the online mode. So
Yeah, ma'am, it's a little bit difficult to have, especially this Bell inequality, to study through the online mode. It's a bit difficult one, but it's very interesting also, ma'am. It's very interesting.
I hope the idea has gone across. I shared the calculations with you in a couple of days, and you can send it to the and the research.
Yeah, that idea is very good. That there, since that wave function is due to the incomplete nature of the wave function, there must be some hidden variable. So we have to look out for that hidden variable. So, but it's something new for most of us, and we have to work out this one to actually feel this inequality. But thank you, ma'am, and thank you for giving us an insight into this hidden variable theory and the Bell's inequality. And we are very thankful to you, ma'am, for all the lectures you have given to us for the past 2 days, and still you have completed that 2 lectures, this one. So in this very short period of time, I think that you have very nicely explained the motivation behind quantum mechanics and why to study the quantum mechanics and what are the foundations of the quantum mechanics. So I thank you very much, ma'am, and I'm looking forward, and in fact, we are all looking forward to interact with you in near future, ma'am. Thank
Before
you
we
very
close,
much.
I want to say something.
Sure, sir. Sure, sir. Sure.
So I just been because we keep the last lecture a bit open,
Okay.
and to keep it means to plan it properly means I just want to understand from the participants what kind of queries they have from all the lectures which has happened so far.
Okay, sir.
So
Okay,
if the
sir.
participants can share, that means what kind of queries left, which things you need to feel repeated or discussed means in the last lecture.
Okay, in lecture 12, we will plan according to that, sir.
The participants can give feedback means what is their expectation from the last lecture.
Okay, sir.
Last
Okay,
lecture
sir.
of the day.
Okay, sir. We will see to it. Definitely. So, with this, we come to the morning session, end of the morning session of third day, and we will join again at 1:45 for the post session. Till then, thank you very much.
Yeah, thank you, sir, for the invitation. And if you can share my email ID with the participants, and if there are any questions, they are always welcome to approach me anytime and ask me in the email.
Okay, ma'am. Sure, ma'am. Sure. Thank you, ma'am.
Thank you.
Sir, good afternoon.
Good afternoon. Good afternoon. Welcome.
Thank you, sir.
Good afternoon, Dr. Meet Kamal.
Good afternoon, sir. How are you, sir?
I'm fine. We are in the college.
Okay.
Dwivedi sir and myself
Uh,
all are in the college, and we are managing the things from the college itself.
Okay. Great.
So, good afternoon. I request Dr. Meet Kamal, Associate Professor in the Department of Chemistry, to begin this session. Dr. Meet Kamal.
Thank you so much, sir. So, a very quantized good afternoon to all of you. A very privileged moment for me to welcome you all in this lecture workshop on elements of quantum information, which is organized by Department of Physics, Christchurch College, Kanpur, and sponsored by Indian Academy of Sciences, Bangalore, Indian National Science Academy, Delhi, and National Academy of Sciences, Prayagraj. It's time to introduce my eminent and diligent speaker of present session, Dr. Anirban Pathak. I welcome you, sir, on this online platform of ours. Dr. Pathak is FNASc FIETE professor in JIIT Noida, a very renowned theoretical physicist, and is a prime member of draft committee of quantum computing of Government of India. He has a wide acknowledged work worldwide in the area of quantum optics with focus on quantum cryptography and has been felicitated with various awards all around the globe. The topic of today's lecture is Introduction to quantum cryptography, where we stand, and how to perform quantum cryptography in the laboratory. I welcome you, sir, once again on this online platform, and I would give this platform to you to enlighten our participants.
Thank you, Dr. Kamal. I'll start my talk, and this is in continuation with my previous lecture, and in the previous lecture, I tried to make a bridge between the lectures given by Professor Misra and the lectures which were supposed to follow on the application. So including what Vijay has told yesterday and Professor Chandrasekhar has told yesterday. So I gave so now this lecture, and maybe if it depends on the participants' queries, that I or Professor Misra will continue with the next lecture, and we'll try to address all the queries and whatever you want to listen, and to make it a kind of complete program. So in this lecture, I'll not only talk about what I mentioned in the topic, I'll try to connect with the other lectures which has happened in the applications. So I start with my presentation, and in the last time there was a problem in changing slides. So if you find that my slide is not changed, then tell me. So this is the first slide. So as you see in the slide, when we show the second quantum revolution, this is a book from where this word originated, and we are now talking about all the second quantum revolution. So I mentioned that we live in a quantum world, and many things are quantum, but many things you can understand in today's technology, for example, your computer or your mobile phone, without much deeper knowledge of quantum mechanics. So these are product of fast quantum revolution, specifically laser and transistor is the product of fast quantum revolution, whereas the kind of technology we are talking about every day afternoon is part of second quantum revolution. So the second quantum revolution uses more weird properties of quantum mechanics, like collapse on measurement, like non-locality. So just now, before my talk, Professor Misra was talking about Bell non-locality and local hidden variable theory. So quantum mechanics is essentially non-local, and if you can exploit that non-locality for certain applications, those are part of second quantum revolution. A quantum state collapses on measurement. So if you can exploit that for certain tasks, say for making quantum random number generator, so these are the counterintuitive properties of quantum mechanics, and now we are in a situation where we can exploit those properties for making technology. And as mentioned yesterday, Vijay told in detail that National Mission on Quantum Technology and Application is almost in a situation to be started, which has a budget of 8,000 crore. A program called Quest has started. So actually there are two programs called Quest. One is of DST and one is of ISRO. And these are already ongoing. So what kind of things are happening? So this is a kind of chip which Vijay was telling yesterday in his talk on how to make quantum computer. So that it's so important that White House has now an office for National Mission on Quantum Computing, a coordination office, and quantum information is not an act, it's a law now in US. So it's so important. So is the slide change? Can you see a slide with my phone number and email?
Yes, sir. Yes, sir. It's there.
Okay.
Your first slide is there, sir, right now. Introduction to Quantum Cryptography.
No. Okay. So then the problem
slide is not changed. Yes.
Okay. So
yes. Now it's changed. A few words before we start. Yes, now it is visible, sir.
So for all the participants, my email address and phone number is here. So if you, even at later stage you have any query, you can drop me a mail. Okay. So as this is before we start. Means, as I mentioned that we'll talk about where we stand. So this is where we stand. So at the top, you can see that there is a stadium, picture of a stadium. So I hope now it's full, means I'm sharing my screen so you can see the stadium. So there is a stadium. This is the stadium for Soccer World Cup, where 2010 Soccer World Cup happened in South Africa. And the information about the players' movement from one place to other place was secret. And they were communicated via a quantum cryptographic line and using something called BB84 protocol. So this was first quantum cryptography enabled stadium, and it's already 11 years old. Now, 3 years back or 2.5 years back, it made a lot of discussion on satellite-based quantum communication. So this is a station in China, and there is a station in Austria. And here is so through the satellites, they were able to establish an unconditionally secure key, which is created by quantum resources. So the satellite is a conventional satellite. It carries some devices which is called payload. So anything that a satellite carries is called a payload. So the payload was enabling quantum communication, and a key was using quantum resources. A key was created between China and the satellite, and another key was created between the satellite and Austria. And then the satellite did that. It make a XOR of both the keys and announce it. And once it is announced, then China does another XOR with his own key. So key of China, XOR key of Austria, XOR key of China will give you key of Austria. So now the Austrian key is available with both China and Austria, and then they can use that key to communicate. So this was a quantum long distance video conference which happened between China and Austria using quantum security, and that draw a lot of attention of the people. So post this, many people, many countries are trying to make their satellite-based quantum communication, including Singapore, who are a bit ahead. And we already have the most complicated task of the satellite technology. We just need to design payload, and there are efforts in that direction. Now, here is a quantum computer where my mouse is. It's called D-Wave. D-Wave is a Canadian company. And this quantum computer, all are superconducting, but this is a bit different technology. It's an ensemble-based quantum computer. And from Amazon Web Service, you can get free access to this for certain tasks. This device is called Clavis 3. This is a commercial device sold by ID Quantic, a company in Switzerland. It's a commercial quantum cryptographic solution. Now, this one is the backend of IBM quantum computer. I have mentioned about this quantum computer in the previous lecture also. And what Professor Vijay Raghavan has described in his structure, kind of a structure. So these are transmon qubits. There are 5 qubits which are noted as Q0, Q1, Q2. This is describing a topology, and in this topology that Q3 can be the control of the control gate and Q2 can be the target. So which one can be control and which one can be target is shown in this topology. So what Vijay was telling was a different topology. He was talking about a ring topology which he has proposed. So at the end, he told about his archive paper. So what is the advantage? So in this particular case, Q4 and Q0 are not connected. So if you have to apply a control NOT gate between Q4 and Q0, I have to do it via QT. But Vijay was telling that he has a new architecture and topology in which the qubits are connected in a circular manner, and then each of them can talk with each other. So that was interesting. And here is another quantum computer called Rigetti. So these are different possible, and then you have Google. And so Rigetti and D-Wave can be accessed via Amazon Web Service. And IBM quantum computer, you can just go to IBM Experience and use your Google ID and access it. So as I mentioned, that the second quantum revolution is something which we are going to happen. We are currently in the midst of a second quantum revolution. The first quantum revolution gave us new rules that govern physical reality. The second quantum revolution will take these rules and use them to develop new technologies, including quantum cryptography, quantum computers, and such things. So what was the use of first quantum revolution? So first quantum revolution allowed us to understand fission and fusion, so the nuclear power, semiconductor electronics, band theory, tunneling. That's the reason means you can you can use this computer. So in some sense, if it was not quantum, the word means quantum means discrete. So it was, if the energy levels were not discrete, there was no semiconductor and you would not be able to use this semiconductor based technology, including your phone, the computer which I am using. Unless there was a laser, you could not have this kind of communication which is allowing us to talk. And even the transparency, the fiber is transparent, a glass is transparent. You cannot understand why a glass is transparent without invoking quantum mechanics. So you see, a metal is not transparent. Why it's not transparent? Any photon you give, whatever be its energy, there are free electrons which will absorb and increase its kinetic energy. But a glass, which is an insulator, if you give a light, then the light does not, visible light does not have enough energy to excite an electron from ground state to fast excited state. So it will not absorb. So if it is not absorbed and it's not scattered, then it will pass through. So that's what happens, that all the transparent materials which you see, except the metamaterials, all the transparent materials which you see in day-to-day life, they are insulated. So how do you understand that? That the metals are conductor and metals are opaque and transparent materials are insulated? It's because of their energy gap, band gap. So, and it's because of quantum mechanics, the energy levels are discrete, and that's why there is band gap. If all energy were possible, there was no band gap. So second quantum revolution is responsible for quantum key distribution to LIGO. So many of you may be aware of this interferometric experiment, which was able to detect gravitational wave. So that's nothing but a Michelson interferometer, but in the one port you give a laser, in the other port you give something called squeezed vacuum. So in this course, we have not spoken about quantum optics, but a squeezed state is a very common thing in a quantum optics. And that's a quantum optical state that you, in Heisenberg uncertainty principle, tells you that if you have two quadratures which do not commute, you cannot measure them simultaneously with arbitrary accuracy. But you can increase the measurement accuracy in one quadrature at the cost of other. So that's the thing which is done in LIGO, and that's used for measurement. So now, this is again summarizing the whole picture. So in quantum information science, which was all the things which we are discussing in the second half of every day is limited to this. So there are three parts mainly. One is quantum metrology or quantum sensing. So quantum mechanics allows you to do very precise sensing. So that can be used for quantum radar. That can be used for gravitational detection. Means it's like a thermal image. There will be a map of gravitation, means where the mass is more. And that can detect submarines. So far, at the moment, we cannot detect submarines. So if a country has one submarine and another country has 10 submarines, they're more or less equally powerful because the other country sharing the border does not know where is that single submarine. But when the submarine will be detected, then the power balance will be disturbed. So many kind of sensors, means handheld NMR to, means handheld MRI machines to, many things will be possible because of quantum sensing. Main task in quantum computation is to beat decoherence. So yesterday at the end of lecture, means in both the lectures, and Lindbergh equation appeared. So Lindbergh equation speak about open quantum system. So us, we teach normally closed quantum system, a particle in a box and nothing else is there, but there are atmosphere, there are environment, everything other than the system is its environment. So that affect, and in the last lecture also I told that may lead to undesired collapse or change in the state. So this is what is decoherence. So we make a qubit, we make a state, quantum state, maybe more than one qubit, but we could not keep it for long. So if there is a coherence time, so if I can keep it for 1 millisecond, all the operations that I have to do it in that time. So if the quantum state is stable for roughly say 1 millisecond and each operation takes 1 microsecond, then I can apply only 10 to the power 3 operations or 1000 operations. So making a scalable quantum computer is very difficult at the moment. But quantum computers are approached with different technologies, optical, ion trap, NMR, superconductive. So the last lecture of yesterday was focused on superconductive quantum computer, but he also mentioned about these different possibilities. The other aspect is quantum communication. So quantum communication is that you can go from one place to other place. So it requires optical means preferred qubit is optical qubit because it's easy to send photon from one place to other place. And that has two aspects. One is secure communication and one is where security is not needed. So one example of the communication where security is not needed is teleportation. So this classification was discussed in Aditi's lecture, and Aditi mainly focused on these aspects, that teleportation or where security is not needed. I have also described the teleportation circuit. Now I will talk about secure communication where the security is unconditional. So first we have to understand what is unconditional security, how it is different from classical world. And commercial solution for this part is available, but not of quantum computer, but there are some small scale quantum computer which you can access online. So here is a list of companies which sells commercial solutions, and you will be happy to see that there is a QNew Lab, which is an Indian company in Bangalore. They are selling quantum cryptographic solution, and the only one company in India. There are several startups, but some are doing just started, some are doing relatively better, but they have commercial products. And ID Quantic is much matured. They have even sold a solution for conducting election whose security will be, say, internet voting kind of thing, or postal ballots will be handled with quantum security, and they sold a quantum solution to government of Geneva, local government of Geneva. So room temperature, single photon detector, QKD systems, etc. are sold by Toshiba, Mitsubishi Electronics. There are many companies who sells this kind of product. There is something interesting. The protocols are designed, and the time for protocol to their realization is very fast here. So here I give an example. Early 2015, University of Geneva broke the record of long distance QKD experiment using coherent one-way protocol. This is called COW, C-O-W, uses decoy qubit and variant of BB84. So I'll come to what is BB84 and 007 kilometer. October 2015, in the same year, that was appeared in a ID Quantic's commercial product. So this is so fast. Here we are showing that the end user is classical. So there may be a situation that end user is classical or using a phone. Now Samsung has introduced such a thing. But the in-between the security is quantum. So that's a particular interest of, and that's called semi-quantum cryptography, where end users can be classical. Well, now these are the things, including teleportation, which can happen in the quantum world. So I ask a question: do we live in quantum world? Yes, of course. And this logic I have again and again told that the word quantum means discrete, and unless we consider discrete energy level, I cannot understand many things which happens around us, including the semiconductor, why the glass is transparent, and so many things. Now, quantum mechanics has various no-go theorem. So what the no-go theorem means, that this you cannot do, that you cannot do. So it's just like, for everywhere there is the limitations, and people were very unhappy in the early years of quantum mechanics. Many people thought that these are limitations of quantum mechanics. But then we gradually realized that these limitations can be exploited, and quantum cryptography is the art of exploiting these limitations of quantum mechanics. So what are the so-called limitations or no-going theorem? So for example, I tell you Heisenberg uncertainty principle. If there are two operators A and B, and if they don't commute, I cannot measure the physical observables corresponding to operator A and B simultaneously and arbitrary accuracy. So you know that you cannot measure position and momentum in the same direction, say x and bx in the same direction at the same time with accuracy. So that's a restriction. That's a no-go theorem. So similar no-go theorem, which are important for us, is one is called no cloning theorem. What does it mean? An unknown quantum state cannot be cloned. You cannot make a Xerox copy of an unknown quantum state. If I give you a quantum state, alpha get 0 plus beta get 1, and I don't tell you the value of alpha and beta, you will not be able to copy it. Why is it so? Suppose you think in another way. You think that I can make a copy. So if I make a copy, then I can measure. If I make multiple copies of it, then I can do a quantum state tomography, or I can do many measurements and find out alpha and beta. Even not, if I have two copies, so one copy I will measure the position and another copy I will measure the momentum. So Heisenberg's uncertainty principle will be violated. So since Heisenberg, you can visualize it as a manifestation of Heisenberg uncertainty principle, that, and this is called no cloning theorem. So what is its impact? So all in quantum communication, always the communication happened between Alice and Bob. So recall the lectures, fourth lecture of the first day, where Aditi was talking about teleportation and telling again and again that its communication happens between Alice and receives. So I have also told that in my first lecture. So Alice is the sender, Bob is the receiver. And in between there is a Eve. So Eve is called eavesdropper, who is trying to get the information illegally. Now, since the quantum state cannot be copied, Eve cannot make a copy of the qubit which is going from Alice to Bob and wait for further discussion and then decide to measure. So if he has to do anything, he has to do a measurement on the qubit while it is going from Alice to Bob. And if he tries to do that, the qubit will collapse. And when the qubit will collapse to one of the possible states, it will change. Suppose I am sending alpha ket 0 plus beta ket 1. Since Eve cannot make a copy, Eve will do a measurement, and if does a measurement, it will collapse, say in 0-1 basis, it will collapse either to 0 or to 1. And if he will reproduce 0 and send it to Bob. And now, on comparison, Alice and Bob will be able to reveal that the state has been changed, so eavesdropping has happened. So in simple words, eavesdropping will leave a trace. But in the classical world, when something goes, when somebody tries to tab your phone or copy your message, you don't get any trace of that. So that's the difference, that any eavesdropping effort will leave a signature and the signature can be detected. So when I make a key, first I make a secure key and then I encrypt a message using that key. So at the key level, if I find out eavesdropping, then I don't use that key. And if I don't use that key, I don't lose any information because I have not communicated any information. There is no broadcasting theorem. So no broadcasting theorem means you cannot send a same message to many people. So if it is a quantum message, this is quantum no broadcasting theorem, quantum states cannot be broadcasted. So broadcast means, just like now I am giving lecture and you are 30 different receivers or 40 different receivers and you all are getting the same information. So you cannot send an unknown quantum state in this way because that would have been cloning, because if you could send to Bob 1, Bob 2, Bob 3 the same qubit, then that means you have made 3 copies. So if we were allowed to clone, we could have made 2 copies of a state and measure position using 1 copy and momentum. So absolutely fundamental concepts of cryptography. So this is important. So one is called Karshav's law. If key is secure, then the encoded information crypt system is secure. So I don't need to discuss about the security of the whole system. So if I can make an unconditionally secure key, which I'll show how to make it, then my cryptography is secure. So what is a key? Suppose your message is something like 001001 and so on. And you have a key of the same size. Suppose your message is of 6-bit and you have a key which is random. If it is not a random, then somebody can guess it. So if it is 11001 and so on. So with the message, you bitwise XOR the key. You write the message, just below that you write the key and every bit you XOR. So 1 XOR 1 is 0, but 0 XOR 0 is also 0. So if somebody does not know key, looking at the output, he will not be able to find out what was the message. But if you have the message plus key, which is called crypt, and you do XOR again with the key, then it will open. Say, just think that. Suppose there is a 2-bit one. So you have 01 is the message. And your key is 10. So 01 XOR 10 will be what? Tell me, what is 01 XOR 10? What is 0, 1 XOR 1, 0? Anyone? Just write below 1, 2, and yes. So now you add, it is 1, 1, and now you add 1, 0 again. So you will get back your message. So if you have if Alice has a copy of key and Bob has another copy of key, and now there is a crypt, and if the key is known, then the message can be discovered. So key is simply a random number which is shared by 2 or more parties. So first we need to generate a sequence of random numbers, and then we need to a scheme to distribute that scheme. So if we can do that, and with the unconditional security, that will give me the quantum key distribution. Classically, we cannot have a true randomness. So this is something I told in the first lecture, that classically, whatever we do, say, I'm tossing a coin. So if I know how much pressure I'm giving by my finger, what is the air drag, etc., then I know what output of Newton's equation of motion only. So there are many parameters. I leave some parameters, and that's why it appears, give a kind of apparent randomness. Classically, but in quantum mechanics, the whole thing, the state collapse of the state on measurement itself is intrinsically random. So quantum mechanics is the theory of quantum mechanics by construction has a kind of intrinsic randomness, and we can exploit that. So wave function collapse or state vector reduction principle is used. Uncertainty principle is used. So uncertainty principle gives me, one cannot simultaneously and accurately measure the values of two non-commuting observables. So, and it also gives me no cloning theorem. And if you try to do measurement, it collapses. So these all restricts if. So initially what I thought that it is restriction of quantum mechanics is now restriction of if, and that gives me permission to do unconditionally secure quantum communication. So before I go to that, means this is a kind of lab, how we do things in the lab. So I continue. So here is a laser. So laser gives a Poissonian photon statistics. And now there is something called neutral density filter. So if you do with a fiber, this one is replaced in the lab by something called variable optical attenuator. Normally people write it like VOA. So I choose the filter in such a way that the neutral density filter is not just like any other filter. This is a filter which reduces the number of photon, means it reduces the intensity, average number of photon, but without changing the photon distribution. The photon distribution has a Poissonian statistics here. It remains Poissonian statistics, and we make it like average photon number mod alpha square, something like 0.1. So that means most of the time I will have 0 photon. Whenever a photon comes, that will be 1 photon because the average is 0.1, and hardly there will be some situation when there is a 2 photon or 3 photon pulses, but it will never come 4 or 5 photon because then the average cannot be 0.1. So it's a weak coherent pulse. So a photon state is a coherent state. You make a neutral density filter. So this is an approximate single photon source. So I repeat, it's not an actual single photon source. It's an approximate single photon source. You can make better single photon source using quantum dot. You can make a better quantum single photon source using a process called spontaneous parametric down conversion. You send a light and 2 photons, twin beams are created. One is called signal and one is called idler. You apply a detector, you measure one, then the other side will have a photon. So this process is called heralding, but we are showing a simple process. So you have a photon which is a single photon. Single photon goes through beam splitter, so it passes in both paths. So it's simultaneously present here as well here. So if this beam splitter is 50-50, here is a qubit which is 1 by root 2 0 plus 1 by root 2 1. What is of its use? So I have made a qubit. Now I apply 2 detectors. One is called detector 0, one is called detector 1. So, although the qubits are present in both, so showing that the collapse measurement postulate that it collapses into one of the possibilities, never both the detector will click. either this detector will click or this detector will click. So when this detector will click, I will note 0. When this detector is click, I will note 1. And if I can, so we have detectors and in the lab, and the detectors are connected to some electronics which is called FPGA. So that registers the sequence of zeros and ones, and I get a random zeros and ones, and that's called random number generator. And this is the thing which is used in ID Quantic's commercial product called Quantis. So if you want random number, quantum random number, you can even download it from. There are places where people can give you permission to download quantum random numbers or random numbers generated quantum mechanically. So is quantum random number word, even Rajnikant does not know what will happen next or which detector will click. So here is the product. So this is a commercial product, and it's the cheapest commercial product. Its price is of the order of $1,000. And we have one in our lab, so many people have a copy of this. And this is just like this looks like this has many versions. There are some card. So card you can put in the PCB slot, and there are USB quantum random number generator, and it looks like the one which we have, looks like your hard disk or laptop charger, and there is a USB connector. You connect with your computer, and you can generate random numbers. So inside that, the kind of optics I described is present. So this creates a quantum random number. But random number alone is not sufficient. This random number will be produced locally. It will be produced to me. But I want to communicate with you, then you must have this copy. So how will I send this copy in a secure manner so that nobody can see it? So, and I'll do this through public channel. So I'll discuss the method which I'll follow is known to everybody. It's not like that I'll write a lot of random number fast, make a book of random number, and someday you will come secretly to my house and I will give you that book, and you will carry secretly that book, and then one morning I will tell, okay, today I will use the 3rd page. So we'll use the key written in the 3rd page. Tomorrow will be the 5th page. And if in between somebody comes to your station and takes the book, then we are gone. Means we will not know that I'm talking to whom, and my enemy can get the key. Suppose you think that two countries are fighting and one particular camp is captured by enemy. An enemy will take that book, and enemy will start communicating as if that their army people are communicating. So that's not desired. So private key cryptography is not something which we do now. What we do is public key cryptography. We'll discuss everything publicly. The protocol will be known, but still I'll be able to generate secure key. So I will deviate a bit because I have opportunity to use part of the next lecture also. So now the idea was that to give you some exposure of the lab. So before I really describe the cryptographic protocols and how I do quantum cryptography in the lab, I'll tell you some simple optical component that we use in the lab. So this is something which I told you in the previous lecture also, that you can use a wave plate, and you know that if in a wave plate, when the light comes, light breaks into two pieces. One is ordinary light and one is extraordinary light. So there are two refractive index, mu O and mu E, and for each lambda these are different. So when a light of wavelength lambda is coming, and you know mu O and mu E, and it's the thickness T, so one travels mu O times T, the other one travels mu E times T. So E stands for extraordinary, O stands for ordinary. And the path difference created is mu O difference mu E times T. And if that is lambda by 4, it's a quarter wave plate. That is lambda by 2, it's a half wave plate. So that's how you decide the thickness. So thickness T for a half wave plate is lambda by 2 mu O difference mu E. So which is very specific to a wavelength. So what is half wave plate for a particular wavelength is not a half wave plate for another wavelength. So every optics that you buy in the lab is specific to wavelength. Now you have heard of a beam splitter. So there are different kind of beam splitter. So one, the conventional beam splitter. So any glass plate is a conventional beam splitter which reflect partly and transmit partly. So in Michelson interferometer we have used 50-50 beam splitter. So we don't need unless I am doing a research level experiment, I don't need a very accurate beam splitter. But this kind of beam splitter is independent of polarization. So normal beam splitter. And then there are two parts, symmetric. So these are normal beam splitter, which is written as BS, symmetric and asymmetric. So symmetric is 50-50, anything other proportion is asymmetric. Then there is something called polarizing beam splitter, which is very useful. So polarizing beam splitter looks same, but it has a property that if horizontally polarized light come, it allows it to go. And if vertically polarized light come, it will reflect. So if I place two detectors, one along the transmission path and one along the reflection path, so whenever horizontally polarized light will come, so the light detector which is in the direction of the transmission will click, and when vertical light will come, then the reflected path will click. Now suppose you have created a sequence of photons, random sequence of photons. Some are polarized in horizontal direction, some are polarized in vertical direction. So horizontally polarized light we are calling 0. Vertically polarized light I am giving a name 1. 45-degree polarized I am calling plus. So a 45-degree polarized light, if you think in terms of a state vector, so this is like 1/2 √2 horizontal plus 1/2 vertical. Because if you send this light, you know the Malus law that a 45-degree polarized light with cos square theta intensity, it comes in the horizontal path, and cos square theta, it will come in the cos square 45, it will come in the vertical also. So here theta is 45 degrees. So in quantum mechanics, you can write this 45-degree polarized light as 1/2 horizontally polarized plus 1/2 vertically polarized. So now if you pass this through PBS, then randomly either the detector in the transmission side will click or the detector in the reflection side will click. So either 0 will click or 1 will click. So if you create a random sequence of 0, 1 and plus minus, or random sequence of horizontal, vertically polarized and diagonally polarized light, you cannot measure them simultaneously. But how can you measure them at all? So if I have to measure 45-degree, 135-degree polarized light, what I will do? So I will apply a polarization rotator. So I'll apply a wave plate kind of thing, which will rotate by 45 degree. So when the polarization is rotated by 45 degree, my 45-degree polarized light will now become 90 degree. So it depends on I'm rotating clockwise or anti-clockwise. So 90 degree is vertical, so the detector 1 will be clicked. And if I rotate it by 45 degree towards the horizontal, so it will become horizontal, and then 135 degree was become 90 degree. So a 45-degree polarization rotator will make it horizontal vertical. And once it is horizontal vertical, then I put a polarizing beam splitter, I'll be able to know. So I have two kind of setup. One setup measures in plus minus basis, or 45-degree, 135-degree basis, which is called diagonal basis. And I have another kind of apparatus which measures in 0-1 basis. So the 0-1 basis measurement is simply a polarizing beam splitter and two detectors. And diagonal state basis measurement is simply a polarizer rotator followed by a polarizing beam splitter and two detectors. And then there is something called polarization dependent beam splitters. So which are for different polarization, it have different, just like here, this is a special case because for horizontal, the transmittivity is 1 and for vertical transmittivity is 0. But you can have different amount of transmittivity and that will be polarization dependent beam splitter. All these things can be written in terms of matrices. So this is what we do in quantum computing. So you have seen the gates, I'm writing the gates in terms of quantum matrices. So a beam splitter can also be written in terms of, so what you need actually to describe a beam splitter, you need two transmittivity and two reflectivity, which are also interconnected. So reflectivity and transmittivity when the light is approaching from the top and when light is approaching from the down. So you can express it in terms of a matrix. So this is the matrix of the beam splitter. So if you put theta is equal to pi/4 or R1 T1 is equal to 1/√2, you have a 50-50 beam splitter. That's a symmetric beam splitter. This is a beam splitter in general. Any computer program can write this and I can check my circuit. So what is a mirror? So mirror is a beam splitter where reflectivity is 100% and transmittivity is 0. So if I put reflectivity as 1 and transmittivity as 0, I get a mirror. So now suppose you have a Mach-Zehnder interferometer. So what happens in a Mach-Zehnder interferometer? Here is a beam splitter, light goes, reflect in mirror, light goes to another beam splitter. So either light goes from this path or it goes from this path, and in one of the detector constructive interference happens, in another detector destructive interference happens. So this experiment is very crucial for understanding of quantum mechanics. A Mach-Zehnder interferometer, if you visualize terms of single photon, it can give you the real feeling of quantum mechanics. How? Let's see. Suppose I send a single photon. And I mentioned that the photon is simultaneously present in reflected path and transmitted path. And when I put detector, either this detector click or this detector click. Okay? So this click is random. And I'm claiming that the photon exists like a wave. It's a superposition of these two paths. But if somebody comes with a model that, well, the photon is like a ball. So half of the times, that's just like classically you are drawing a ball, there are blue ball and red ball, and you are taking randomly from a bag. So either the ball goes with a 50% probability here and 50% probability here. It never goes to both the paths. It's never in superposition. Still, the statistical data which I obtain that either this detector click or this detector click, in total this detector click 50%, this detector click 50% will match. So I cannot still identify that the photon really behave quantum mechanically or superposition of state is possible. But superposition is a wave property and that does not have a which path information. So if I send a photon, classical theory will tell me, the ball-like theory, that if I send 100 photons, 50 of them follows this path, 25 will go here, 25 will go here. 50 of them will follow the lower path, 25 will go here, 25 will go here. So 50% of the time this was supposed to be click. But quantum mechanically I found that 100% of the time this detector is click. So how I can explain it? So here is a photon. The photon goes 1 by root 2 0 plus 1 by root 2 1. Then in one path destructive interference happens, in one path constructive interference happens, and this you can understand in terms of Stokes' law. So this is a quantum interference between the different paths. So quantum interference between the different possible paths, and this experiments clearly established the idea that it travels through, it simultaneously remains present in both or follow a wave-like character. So you want to see this mathematically. How will you do that? How will you do that computation? So I have already written, so this is a mathematical code. So this is how you can define ket. So 1 is the element in the first row, 0 is the element in the second row, and this whole thing is a matrix. So I define ket 0, ket 1. Just take a transpose to define bra 0, bra 1. Define my beam splitter, which is a matrix mirror, and we know that how the state was going. Ket 0 operated on beam splitter operates on ket 0, then there was a mirror, then another beam splitter. So if you write 0, I'll see that the output is coming to be 0. And if you write 1, output is coming to be 1. So this minus sign is a global fetch, it does not have any meaning. So we have seen that if I give 1, I'm getting 1. So only in one path it is coming. So far, still this is a computation only. And when my teachers told me, I had no option to believe my teacher or the textbook. But now you can check that this really happens. So where you can check in IBM quantum computer. So beam splitters are quite similar to Hadamard gate. So you can apply a Hadamard gate, and the mirror is taking the path to take it back into Hadamard. So you put two Hadamard gates, pass a Hadamard gate, and check that for each strike whether it's going to 0 and 1 or not. Then after the Hadamard, you put another Hadamard, and you can make a Mach-Zehnder or mimic a Mach-Zehnder and check that whether this kind of things are happening or not. So now you have more freedom than what we have as a student. You can do many laboratory experiments using IBM quantum computer, and you can run the IBM quantum computer practically in your mobile phone. So I'll speak PDBS. So this is a beautiful thing. This is a polarizing beam splitter, PBS. Now you see, if the horizontal light comes, it passes through. The vertical lights get reflected. Now from two sides, I am giving two photons which are correlated. So just like a Bell state has been discussed many times in the application part. So Bell states are like 0, 0 plus 1, 1 by root 2, or 0, 0, 0, 1, 1, 0 plus minus sorry, 0, 1 plus minus 1, 0 by root 2. So the singlet states also. So now I want to identify. So I'll not be able to identify the plus minus sign, but I'll be able to identify whether it is a 0, 0 plus minus 1, 1 state. So that's a parity 0 state. Because if you add both the bit XOR, you will get 0. Or it's a 0, 1 plus minus 1, 0 state. How? You take this lab. In the lab, you put a polarizing beam splitter and put two detectors. If horizontal light is coming from this side as well as this side, so this will pass, and here is my detector 3, and here is my detector 4. So if I send horizontal, the light comes into both the detector. But if I send vertical, then also light comes in both the detector. So if I send HH plus minus VB by root 2, HH, so a parity 0 state, both the detector will click. But the moment you send HV, so V is reflected, H is transmitted, or H is transmitted, V is reflected. So both the photons will go in the same detector. So if you just pass through a beam splitter, you can identify the given state is parity 0, if it is a Bell state, or it's a parity 1 Bell state. So it's a single optics which do this kind of thing. So how does optics look? So this bench is called optical bench, and these are vibration-free table in the lab, and these are mount, and these tables are called honeycomb table. So these are magnetic, so you can directly attach the mount here, and this is where we do. So this is not picture from my lab, this is picture from one of the collaborators' lab, but we have similar table and setup in our lab too. So you see, the beam splitter and polarizing beam splitter look same, so they're like a cube, but they do the different things. But there is something called beam displacer. So if you send a set of photons, horizontally polarized light follows a path and vertically polarized follow different path. So in polarizing beam splitter, they were perpendicular, but here they are not perpendicular, they are parallel. So otherwise it is working like a normal polarizing beam splitter. It is just separating the horizontally polarized component and vertically polarized component. So if you choose horizontal polarization as your gate 0 and vertical polarization is your gate 1, so it's just taking the 0 component and 1 component separate. So this also looks good. So now, where this knowledge will help you. So I show you, this is a paper in PRL, Physical Review Letters is one of the top journal, and you want to understand this kind of optics. So I have not done any kind of complicated thing. So you know, these are two lasers. So only these mirrors are converting these lasers to TP-KTP crystals. Then here is this kind of things are, so you have written that which one is beam splitter and which one is polarizing beam splitter, although it's drawn similarly. So this is neutral density filter. So now you know what neutral density filter does, what half wave plate does, a quarter wave plate. Then there is a beam displacer. So in principle, you can understand this kind of structure now. And each of this component can be written as a matrix, and you can find out the output. So you can, of course, it will not be possible for you to teach your students to do this kind of experiment, but they can understand the experiments and they can design schematically experiments. And such experiments, if really can be done, can be published in the best quality journal. So for small projects, these are very nice idea to encourage students to follow this kind of experiments, which is connected to basic optics, and you can do top class quantum mechanics through them, and it does not involve Feynman integral or very complicated perturbation calculations. But a basic understanding of optics can help you to understand this kind of experiments. So there is neutral density filter. I have already mentioned that it reduces intensity without affecting the photon statistics. So now, if a photon goes after this, it clicks in 50% here and 50% here. So if I have two detectors, then what we have is called ID quantic quantics. So ID quantic does something which is not desirable. So in ID quantic quantities, half of the time this they consider 0, of the time they consider this as 0. So when this is 0, this is 1. When this is 0, this is 1. So what is the benefit of doing so? So if we do that, then in the generated random number, always 50% of the same will be 0. So even if the beam splitter is little erroneous, So beam splitter is, instead of 50-50, it is 49.5 and 50.5. Still, I'll have equal number of 0 and 1 in the random sequence I have generated. Okay. So now I do a little more. So these are quantum gates in any case, this beam splitter. So now I put a phase plate. So this is a gate. And this can be, you can view it like just a piece of glass. So what does a piece of glass do? So if you pass the light through it, you remember that otherwise the light should have traveled a path of path t, if it is of thickness t, because refractive index of air is 1. When this is present, the light will travel for a path mu t. So what is the path difference introduced? This is something which we teach in first semester. The path difference introduced will be mu t. Sorry. So now the path is mu t, and then initially it was t. So the path difference introduced is mu minus 1 times t. So t times mu minus 1. Now path difference of lambda is equal to phase difference of 2 pi. So we can find out that how much is 1 unit of path difference means. That's 2 pi by lambda, and mu minus 1 t is then 2 pi by lambda times mu minus 1 t. So that's the value of phi. So introducing phi in one of the path, and phi is nothing but a kind of glass plate. So you have seen quantum gate. You just take a glass plate, that's the quantum gate. You just take a cover of your mobile phone, or you take a biology box glass, that's a quantum phase gate. So what does the quantum phase gate do? It introduces a phase phi in path 1 and no phase in 0. So this is the path 1 and this is the path 0. So this is nothing but a Mach Zehnder interferometer. And if you apply that, then the probability of detecting here becomes sinus phi by 2. Probability of getting it here is cos square phi by 2. So if phi is equal to 0, you will see that only one detector clicks. So how this happens? So each of this is a gate. You can write their matrices. So this corresponds to this matrix, this corresponds to this matrix. So this is a gate, which is a non-Hermitian gate. So e to the power I phi is introduced on 1. You can see it easily. So in the last time I talked about the jet gate. So in jet gate, here you put pi. So this will be minus 1. That will be jet gate. Then we show in IBM that there is T gate and S gate. So this is phi is equal to pi by 4 and phi is equal to pi by 2 gives you those gates. So different value of phi gives me different gate. So that means here is a glass plate whose different thickness will give me different gate. So just like the way I was doing quantum circuit in previous lecture, so the state 0 is 1 0, gate 1 0. You have a beam splitter, you write it like this. You have a phi gate, you have another beam splitter. You write all of them, you know what will be the output. So I'll not show this. So this is a computer. What is NOT gate here? So the NOT gate is a laser pulse. The pulse which can take a light, which can take the electron from ground state to excited, is a NOT gate. Okay. So I'll introduce another optical component which we use in the lab. So this is called pentaprism. What is a pentaprism? Pentaprism, what it's doing, a light is coming and you see that it returned the light in 90-degree direction. So it just comes, it goes like this, and it returned in 90-degree direction. So do you remember that you need this kind of things in the lab? The answer is yes. So normally I place a mirror in 45 degree. So if I place a mirror in 45 degree, then the incident angle and then angle of reflection will be equal. So light returns in 90 degree. But placing a mirror in 45 degree is very difficult. So where we are doing? So you see, in all this beam splitter business, we are putting it in 45 degree. So I have an interferometer. So all these mirrors are in 45 degree. If it is in 45 degree, then only the return part will be 90 degree. So I can replace this by pentaprism. So life will be easy, setting up will be easy. So when you have to realize a Mach Zehnder interferometer in the lab, you will use pentaprism in place of mirror. So this is the pentaprism picture, and this is another paper from PRL where pentaprism is used. So these can be understood. So the lambda by 2 is halfway plate, lambda by 4 is quarter wave plate. So when you teach polarization in first year optics, you teach it so, you teach the beam splitter. We teach Mach-Zehnder and Michelson interferometer. So just see that a pentaprism is put here, and rest of it's nothing but a Mach-Zehnder interferometer. So now we will be probably able to get them connected to best quality quantum information experiments or optical realization of them. And then there is something called retroreflector, or a corner cubes are commonly used to produce a delay. A retroreflector reflects back any incident ray from the source along a path which is parallel to the incident ray. So let me draw a picture. So if A and B goes directly, the path is 5 meters. Now A comes, hit a mirror which is placed at 45 degrees. It goes here, it return back. So this is a corner mirror whose angle is 90 degrees. So this can be replaced by retroreflector, and it comes back. So then it has traveled additional 5 meter plus 5 meter, 10 meter, and whatever time is required to travel 10 meter, that much is the delay I produce. One of the problem in quantum mechanics now is that there is no quantum memory. So I cannot store quantum state and in a memory, and I can take out whenever it is needed. So what we do, we give a delay. So delay helps me to extract the information, but not whenever we need, only after a fixed time. So look at this paper again. So this is again another PRL, and you see what they have used. So this triangular thing is retroreflector. This is a polarizing beam splitter. What it is introducing? So it was a path T, and this is T times 3 nanosecond. A delay of nanosecond has been introduced here. Now, there is a beautiful thing called circulator. So in circulator, we often use in the optics, especially in the fiber optics kind of experiment, light comes from path, and if it is a clockwise, if it comes from port 1, it will go to port 2. But if it returns from port 2, it will go to port 3. So it follows a sequence. So if the light goes and it reflected back, it will not interfere with the original path, it will go here. So its applications will be clear. Now, I come to interferometer. So different kind of interferometer is used in your different kind of interferometers are used. We teach in first year optics. So first we start with the condition of interference. So condition of interference is that if the light comes, even they must be coherent. So how do we make coherent sources? We create two sources from one. So one of the ways that you put a beam splitter is the reflector, one is the transmitter. They must be coherent, but they will never meet. So how to make them meet? So I put two mirrors. So this mirror will reflect, this mirror will reflect, and there is a beam splitter. So they will interfere here. Similarly, so this is what is this? This is nothing but a Michelson interferometer. Now, if I do, the light goes like this, and instead of sending them return exactly in the same point, I make them 90 degrees. So this goes 90 degrees, so they can meet in S. So, but I put a beam splitter to see the interference, and we have seen in the Mach-Zehnder interferometer that this one clicks, this one does not click for single photon case. So this is my Mach-Zehnder interferometer. But there was another way. So instead of sending both of them in this way, I can put a beam splitter, a mirror here and a mirror here, and ask both the beam to meet at this point. Well, so this also have a name. This is called Sagnac interferometer. So it's easy to understand this interferometer. And it's even more easy to realize them in optical fiber, because in optical fiber, you don't need the mirror. You just bend the fiber, and then you can ask them to superpose. So wherever there is a beam splitter, that's replaced by an optical coupler. So a coupler works like a beam splitter. They are mathematically equivalent, and we often use them. So here we come to their practical application. So one of the beautiful things, I have a setup in the lab, but it's a Michelson interferometer based setup. And this kind of experiment you can include in your syllabus. You can teach your student, because many of you have Michelson interferometers, and in proof of principle experiment, you can show something called Elizar-Hedman bomb testing experiment. So that's a counterintuitive experiment. It's very, very interesting. So let me describe the experiment. So here is a source, and it's a Mach-Zehnder interferometer. So if nothing is there, there is no absorber or bomb, then the detector D2 clicks. Now, here is a bomb, and the bomb is such that when a photon comes, it blasts. And if there are there are two kinds of bomb. There are active bomb and inactive bomb. So active bombs receives a photon and blast. So it just give a click. So it looks like a detector. It absorbs the photon. Whereas an inactive bomb just allows the photon to go and it reaches here. Now, our perception is that anything we see is because the photon goes, reflects and come back. That's why we can see something. So I want to see a very peculiar thing. So this is like a detector. So it is detecting that the photon is in this path or not. So if the photon is not in this path, this is here. So I am knowing the which path information. So in wave particle duality, either I know particle nature or I know wave nature. So the moment I know the particle nature, that is the trajectory, the wave nature is lost. So it's no more to exist in both the paths. So the moment it is detected here, it is not detected here, but the detector is present here, then it's like going like a particle. So if I send 100 photon, 50 photon comes here, some of them is absorbed by the bomb and bomb blast. Some of them is not absorbed, the bomb is inactive, they reach D2 and D2 clicks and nothing happens because apparently as if the detector is not present. But there are 50 photons which is going up, and in some of those cases here is an active bomb which looks like a detector. Then the wave nature is lost and it behaves like a particle. 25% of those will go here because 50 of 25 will go here, 25 will go here. So 20% of the active bombs will be detected by click of this detector. So whenever this detector clicks, I know that here is an active bomb. So 25% of those bombs I can detect without really sending even a single photon there. So that's pretty interesting. And our perception or intuition was that only when a light goes and returns, I see it. But even without sending that, ending a light, I can detect the presence of the photon. So this is a non-interactive or interaction-free measurement. A very peculiar thing of quantum mechanics. An interaction-free measurement can be shown with the interferometer-based experiment in the lab. Our third lab sells a apparatus and which costs something like 1.5 lakhs. So for many PG department, it's not a big thing. Now, here is a source. So there is a Mach-Zehnder similar thing, but now this side belongs to Alice, this side belongs to Bob. And Alice and Bob puts absorber. So Alice and Bob puts some absorbers in this side and this side to stop the beam randomly. So sometimes Alice puts, sometimes Bob puts, sometimes both puts, we don't know. So there are 4 possible cases. So both Alice and Bob stops the beam. So when both Alice and Bob stops the beam, none of the detector click. None of them put, then this detector D2 clicks. If one of them put, then half of those cases this detector will click. So now there are 2 possibilities that Alice put and this detector click. Now Bob knows whether he has put it or not. So if he has not put that absorber and D1 click, that means Alice has put, and they have pre-decided that that will be considered as 0. And if the detector clicks and Bob has put, since Bob put, Bob knows that he has kept the detector, and Alice knows that she has not put, so Alice knows that it is because of Bob and call it 1. So at the end of couple of run, Alice and Bob will have a sequence of zeros and ones, and both of them have 0 and 1. Eve will also know which are the successful click, but Eve does not know whether Alice has put or Bob has put. So he has her uncertainty is of 1 bit, and this is a quantum way of generating key using Mach-Zehnder interferometer. There are other apparatus. So this is also using Mach-Zehnder interferometer. This is called Goldenberg-Hedman protocol. So here we create a state Kt plus Kb by root 2, and one of the wave packet goes from the top and one path follows the down. And then one of the path is delayed here and one is delayed here. And then they superpose here. But for Eve, both of this, the path is such that only when Kt reaches here, Kb starts the journey. So A and B are the photons in both the paths simultaneously is never present in Eve's part. So Eve cannot detect them simultaneously, or in some word, Eve cannot do measurement in wave basis. Eve has to do measurement in particle basis only. So Eve will do in Kb basis, and the superposition will be lost, and that will be detected. So even using orthogonal state, we can do this kind of. So there is a similar thing called N09 protocol. You can see the optics. It involves polarizing beam splitter and detectors and the delay, which we have already described. This is called N09 protocol. So counterfactual, interaction free, all these things are the bomb the bomb kind of things which I mentioned. So N09 is also, this is a counterfactual measurement. This is an example of where counterfactual cryptography. So this is how a real lab looks. So in the real lab, in a cryptography lab, you have laser beams, you have halfway plate, you have beam splitter. So lights comes and you have, and all these mounts are placed in an optical bench. So I'll skip a few things. Okay, means this is a picture of something which is a pilgrimage of the cryptographer. This is in a place called Poznan in Poland. So there the cryptographer first break Hitler's Enigma code. So there were 3 scientists, 3 mathematicians. So this is a triangular pillar, and in 3 sides those random numbers are written and their names are written. So they know that they were able to break the code and knew that Hitler is coming to invade Poland, and they fled and gave these copies to British and Russians and others. And then in Bartholdi Park in England, Alan Turing made many copies and successfully broke many of the Hitler's code. So when these mathematicians decided the fate of world were a lot using cryptography, of course the classical cryptography. So there are many aspects of quantum cryptography which we do. So we essentially tell that we do IT, information technology, with qubits, and there are many aspects. We do quantum voting, which is voting in a quantum with quantum security. We do quantum key distribution, quantum private comparisons, quantum way of doing auction, and many such things which will appear gradually. Secure things can be divided in this way, that secure quantum communication. So everything is secure quantum communication, and then there's quantum dialogue. So quantum dialogue means with a quantum security, I can talk with you and you can also talk with me. So both way, but normally it's a one way. And when it is one way, then one party only talk, this become quantum secure direct communication. So there are 2 kind of things. One is this deterministic secure quantum communication, and one is quantum secure direct communication. So both are direct communication. One requires some additional bit for decoding of the information. QSDC does not require. Now, if I have ability to speak both ways, then I can definitely speak one way. So in QSDC or quantum dialogue, meaningful informations are sent. So if I don't send meaningful information, then I send a random key, then it becomes QKD. So if you are able to do quantum dialogue and you have a random number, you can sequence, you can do quantum key distribution, because you can send the key in a secure manner. But the opposite is not true. Then there is something called QKA, quantum key agreement. So quantum key agreement is a special task where Alice and Bob equally contribute in generating a key. So in each of the bit, both of their contributions will be same. And then we talk about semi-honest Alice and Bob, etc. and different other kind of problem called, so they belong to a problem called, they're cryptographic problem, but not essentially in communication, they're in computation. So some problems are, in a set of problems are called secure multi-party computation, like voting, auction, and all these things are. So a particular problem is called socialist millionaire problem, where there are 2 millionaires. They want to check that their assets are equal or not. Suppose Adani and Ambani wants to compare that they are equally rich or not, but nobody wants to disclose the exact amount of their thing. So we have to compare, and just one is giving x, the other one is giving y. I have to compute a function f of xy. And if x is equal to y, it gives 1. And if x is not equal to y, it gives 0. But it does not disclose what is the value of x and y. So this kind of things can be done using quantum thing. So I already mentioned Karshov's principle, and now I want to do in the next lecture means the use Karshov's law and design cryptographic protocols, show how it is done in the lab. So I guess I should stop here and take some questions up to this point.
Yes, sir. Thank you so much, sir, for such a lucid lecture. If you permit, we can share some questions with you.
Yes, of course.
There is one question from Shruti Dubey. She's asking that, sir, how is error of measurement reduced in quantum cryptography?
Okay, so we have not prepared slides for that, but there are many limits. Means like, and Heisenberg is one of the limits. So you know that if I'm, as I mentioned, that there are two observable, say X and P or A and B, and they don't commute. Then Heisenberg uncertainty principle tells you that you cannot measure X and P simultaneously with arbitrary accuracy, and then you have some relations like delta X, delta P greater than equal to H bar. But you can do accurate measurement in one of them at the cost of other. So now in the LIGO experiments, in the gravitational wave detection, so when this is a beam splitter and light comes from one side and the other side is vacuum, but vacuum is also made of electric and magnetic field, and there are, if you understand, it's like an electromagnetic wave in second quantization. So you can quantize in two quadrature. So at one quadrature I can squeeze, the fluctuation is less. So at the cost of increase in the fluctuation in other quadrature, and suppose I reduce in magnetic field and I do all the measurements in electric field type, then I'll have a better measurement. So this uses the Heisenberg uncertainty principle and reduces one quadrature, and that helps me to do measurement in better measurement in another quadrature.
I think your query might have been clear, Shruti. There is one more question that Shreya is asking, and she's remarking also that, sir, even some opaque materials are insulators.
Yes, no. That's because of the defects and scattering centers. But what I mentioned, I made a statement that metals are opaque and transparent materials are insulator. But I never meant that all the insulators are transparent. So there are defects. Like I'm sitting on a wooden table. The wooden table is insulated. So there are a scattering center, and the light is scattered in different directions. It absorbs. But the glass is insulator because glass is insulated, so it has a band gap of 6 electron volt or so, and my visible light does not have enough energy to pick it, and that's why it passes.
Thank you, sir. There is one more statement by Amba Nafees that she's saying that the big advantage of quantum communication is it will be tough for the hackers to hack the information, and it will be strongly encrypted.
So technically it is called unconditionally secure. So why it is called unconditionally secure? So first I have to understand what is conditional security. So far in the conventional cryptography or classical cryptography, there is a mathematical problem which is difficult to solve, and we use that to encrypt. Quantum mechanically, there is no such mathematical problem. It will be on the no cloning theorem. It is on the collapse on measurement. Those with physical principle will give the security. So it's difficult to hack, but it's not impossible to hack. So classical sense, it is unconditionally secure. But why? How can we hack? Because this beam splitter will never be a 50-50 beam splitter. So I have a detector which will never be 100% efficient detector. So defects means our lab is actually a quantum hacking lab. So in our lab, we try to do quantum hacking, means we just want to use the device imperfection to hack things. But it's really unconditionally secure in the information theoretic sense.
Okay. Thank you so much, sir, for such a wonderful explanation on quantum computing, the band description idea that you gave, explaining the metals and the transparent materials, and the know-how of the commercial availability of the product, and especially making clone and violating the Heisenberg uncertainty principle. And you gave a very good explanation about the various no-go theorems, the concept of key. And the wonderful part of your lecture was the elaborate explanation that you gave us about the quantum communication experiments, especially explaining the types of beam splitters and the expression in matrices, concept of pentaprism, retroreflectors, interferometers. And very well said that we can allocate certain experiments for our PG students. Thank you so much, sir, for such an eloquent quantum dialogue with us on this platform and sparing such valuable time of yours with us. Thank you so much. I would also like to give my heartfelt thanks and gratitude to Dr. R.K. Dwivedi, Head of the Department, Physics, and the course coordinator of this virtual workshop, for giving me this opportunity to interact with such academic technocrats on this session. Thank you so much, sir. And one thing at the end, I would like to say that after listening to the lecture of Professor Pathak, that it's the time for quantum consciousness now. And I should say that when we say in certain principles or in certain laws that it is impossible, that impossible word now stays nowhere when we come in interaction with quantum computing. And I think now we can simultaneously exist at many places under certain condition, and it is counterintuitive. Thank you so much.
Thank you so much, Dr. Meet Kamal. So, Pathak sir, we will have a break of 10-15 minutes, and then we will meet at 10:3:15.
Okay, 15 minutes. After 15 minutes.
3:15. So we will meet at 3:15 again.
Okay.
We will begin the session as soon as Professor Pathak and Professor Misra joins the session. And this is going to be an interactive session.
Sir, unmute yourself. Unmute करिए sir. No sir, unmute करिए sir. लेकिन यहाँ पे muted दिखा रहा है sir.
Dr. Singh, can you hear me now?
Yes sir, you are clear now. You are audible.
Okay. So, dear participants, Professor Pathak has joined, he is with us, and this is going to be an interactive session. What you can do, you can unmute yourself, open your video and ask questions.
Now we'll go for interactive session per se after half the lecture means.
Okay.
So first part I'll tell something, I'll show you something,
okay.
and then we'll move to. So of course means if they have questions they can ask means before we start.
Okay, sir.
If you have any questions at this moment, first we take some questions, then I speak something, and then I will take some more questions.
Right now we don't have any questions, sir, in the chat box. Sir, we don't have any question right now in the chat box. You can start.
Okay. So, as I mentioned, that Karshov's principle tells that means if there is a secure key, then the cryptography is the crypt, which is combination of key plus the message, is secure. So whole thing is on finding out ways to find how to distribute a key in a secure manner. So how it is done in the classical schemes. So the first, the whole idea was like a book of key, and the key book is kept with somebody. But everything changed in 1976 and 78 when RSA and Diffie-Hellman protocol came. So these are the protocols in which the cryptographic schemes are done in public. When the keys are created through public discussion, the protocol is known, but still it is secure. So for this, there is a background mathematical problem. So what are the mathematical problem? For example, you think about factorization problem. So I give you two large prime numbers and multiply that, and then I give you the product. But I did not tell you that what is the factor. So how will you find out the factor? So you have to do first divide by 3, then 5, then 7, maybe all the prime numbers till root over n, where n is the main number, to find out the factor. So it requires much more step than checking the solution. So if I give you the factor and you know the factor, you can just divide and find out what is the other one. So this kind of mathematical problem, which cannot be solved in polynomial time, are considered to be hard. So, or which requires steps greater than polynomial in n, where n is the size of the. So this belongs to a complexity, and all the problems of same complexity class, same type of complexity belongs to a complexity class. So those which cannot be solved in polynomial time is called NP, or non-reducible to polynomial, and those are the hard problems. So here is a cartoon. A student has got A grade, and he is asking his teacher. The teacher is asking, why you have not done anything? Then the student is telling that all the problems appear to me in NP, cannot be done in reasonable time. Then the teacher say that if you don't study, everything will appear in NP. So this NP problems, where solutions can be checked easily, but which solutions can be checked easily, but which cannot be done, which cannot be solved easily. So they are called NP, and one such problem is factorization. And so there are many classical protocols, and then there is a time which requires to break a code, because if you want to make your cryptography or information which you send is secure for a long time, then you have to use a longer key. So if the bit length is 2048 bit, so normally your encryption is 128 bit or 256 bit, then your key will be secure until 2040. If you use 3106, it is expected to be secure under 2065. But in between, classically cloning is allowed, so somebody can clone and the big computer, then apply Peter Shor's algorithm, which is discovered in 1994, and Vijay told you about it. So that does the factorization very fast. So when it will do fast factorization, and you have already now cloning is allowed, you make a copy and then you can break things. So there are informations which need to be secure for a very long period. Suppose Prime Minister of India has discussed something with the Prime Minister of Israel. So we don't expect that it will be disclosed in 10 years. So it must be kept secret for many more years. So then, even now, when quantum computer is not there to apply source algorithm, it's better to use quantum cryptography. Now, everywhere, so there is another cartoon which will explain you something. So when I solve a problem, there is number of steps required, and that's important. So what is an algorithm? Algorithm is a systematic procedure to solve anything. So algorithms has nothing to do with computer. So you all know that, say, all of us know that how to do addition. So when you learned addition in class 2 or class 1, you wrote the number. Suppose you are doing addition of 12 plus 35. So you write 1 and 2, and below that you write 3, 5. You add 2 and 5 make 7, and 1 and 3 make 4, and you get 47. So then the size of the problem is 2, and you have done it in 2 steps. So if the size of the problem is 3, means there are 3 digits plus 3 digits, you do 3 sums. So the number of steps required, if the problem size is n, number of steps required is n. So this is a polynomial in n. If you do multiplication, you will require number of steps. So in the worst case, whatever steps you require, that decides complexity. So now there is a Grover search algorithm. Yesterday, this is an unsorted database search in quantum computer. Vijay told you about that. So there are 10 to the power 6 names in a telephone directory, and they are arranged according to their name. And now I give you a number and ask you to find out the name. How will you do it? So you have no other option but doing some crude method to search. So one student answered that I have a simple method. I will call that number and ask his name. So that will be done in one search. But that's not the complexity, because that may not work. He may not pick up the phone. He may deny to tell the phone. So when I design an algorithm, it should be such that it succeeds always. Okay. So there are a couple of quantum algorithms. Grover algorithm is one. Source algorithm is one. And this is the one which I was trying to tell you, that if there is a message and there is a key of same size and you do bitwise XOR, that 0 plus 0, 1 plus 1 is 0, then third 0, 0 is 0, and then somebody adds so if this is a symmetric key and this key is with Alice and this key is with Bob, if Bob has the same key, he adds, he gets back the message. So this cryptogram is decrypted or decoded with this code. So you just need to distribute this key between Alice and Bob in a secure manner, and then we can do. And if you see this 0, so this can be coming because of the 0, and when we see this 0, so this 0 has come because both the terms were 1. So I can get in the cryptogram 0, and at that time message can be 0 or message can be 1. I cannot guess anything about the message from the cryptogram. So I'll skip this short history. The historical note is very interesting. So when you write a paper, it's very important that you send it to correct journal. So in 1970, Stephen Weisner wrote a paper on, he has an idea that he will make a non-clonable quantum note. So if you take a currency note, 100 rupees note or 500 rupees note, there are some numbers. So he thought to avoid forging, he will put some qubits in that. So if somebody tries to forge, he has to do a measurement and it will collapse and it will be detected easily. But the problem is that the quantum states are fragile. You cannot put a quantum states on a note and keep that in your wallet. So this will never work. But that had all the idea of no cloning, conjugate coding, and BB84 protocol. So Stephen Weisner was classmate of Charles Bennett, who is founder of all this quantum teleportation, quantum cryptography, everything. And they graduated from same college, and then they were doing masters in different places or PhD in different places. And they used to meet very often. And in some meeting, Stephen Weisner told about this paper to Bennett, and Bennett became very interested. And then the thing is very interesting. In Puerto Rico is a beach city. In Puerto Rico, somebody was swimming, and his name is Gile Brassard. So there was a IEEE conference, and Gile Brassard was swimming, and suddenly he saw that a person is coming close to him and telling him a weird story that somebody has think of a quantum note, a quantum currency note, and its cryptographic application. So the man who came and told that story was Charles Bennett. So Bennett and Brassard started swimming and discussing, and till the point they reach the beach, and they already had the idea of BB84 protocol. So, but this was in 1979 or so, but it took much time to publish it, because that time nobody was interested about this thing. And then there was a IEEE conference in IISc Bangalore, and I was asked to give an invited talk, and Brasar thought that's the idea, that I can give a talk and that will be published, and that's how BB84 protocol was published. Okay, so I start with a basic idea, absolutely basic idea of quantum cryptography. Now you think that there is a state, Bell state. Already you all know that Bell state, 0, 0 plus minus 1, 1, or a singlet state. So the first particle is with Alice, second particle is with Bob. But I don't know whether Alice has 0 or Bob has, but Alice has 0, Bob will have 1, Alice has 1, Bob has 1. Now, Alice created, I'm trying to make a public key cryptography, and we already understand that how symmetric key cryptography works. So Alice created n copies of this Bell state, keep all the first particle with herself, and sell all the second particle to Bob. And then Alice or Bob does a measurement on their respective qubit. So if Alice got 0, Bob will also get 0. If Alice got 1, Bob will also get 1. So in n copies, there will be n bit string, and the string, ideally, the string with Alice and the string with Bob will be exactly the same. So they will have a symmetric key. But life is not that simple. So where is the problem? The problem is that there may be an Eve, and Eve may do a measurement. So Eve does a measurement, Eve will also get 0 or 1, and Eve will make a copy of that 0, 1 and send it to Bob. Bob will get the same thing, because 0 measured will be 0, 1 measured in 0, 1 basis will give you 1. So they will not be able to identify Eve. What Eve strategy they have to take? They have to use more than one basis set. So now, actually 0, 0, 1, 1 can also be written as plus, plus, minus, minus, where plus is 45 degree polarized, 1 is 135 degree polarized, and plus is 1 by root 2 0 plus 1 by root 2 1, and minus is 1 by root 2 0 minus 1 by root 2 1. Okay. Now, plus minus is a basis, that's the diagonal basis, 45 degree, 135 degree, and 0, 1 is a basis. So Eve decided, so Alice prepared the same state, but Bob decides that Bob will randomly measure them in 0, 1 and plus minus basis, and Alice will also do the same thing. So if 0, 1 basis, if both, there will be half of the case when there are two bases only, half of the case their basis will match, and in those half of the case, if Alice got 0, Bob will also get 0, and if Alice got plus, Bob will get plus, if Alice got minus, Bob will get minus. But now, Eve does not know which one will be measured in 0, 1 basis and which one will be measured in plus minus basis. So Eve choose a wrong basis, and Eve, suppose I say prepare in 0, 1 and Eve measure in plus and got a plus, and Alice measure in 0, Alice may eventually get it 1, because this is plus is 1 by root 2 0 plus 1 by root 2 1. So with half probability, so 1/4 of the cases Eve will be detected. So that makes quantum mechanics different. So you just think that Alice prepare a 0, Bob measure it in plus minus basis. So 0 is 1 by root 2 plus 1 by root 2 minus. And then half probability he got plus. Bob again measures it in 0, 1 basis, but Bob with half probability got it 1. So half of half is 1/4. So with 1/4 probability, Eve's effort of detecting it will be detected. So where from the security comes? So here is the origin of security. So there is a picture of mermaid, and teacher asked a student that give me an example of quantum superposition. And the student told mermaid. So mermaid is a half girl, half fish. But teacher told that, but nobody has ever seen a mermaid. Students say, well, when you do a measurement, it collapses either to fish or a girl. But that's a wrong explanation. So like a plus state, when measured in 1 by root 2, so plus state is half 1 by root 2 0 plus 1 by root 2 1. So when you do measurement in 0, 1 basis, it collapses to either to half 0 or to 1. But if you do the measurement in plus minus basis, it will always be plus. So if the mermaid is also element of a basis set, if you do a measurement in that, it will be mermaid. So that's a special basis when you can do measurement. So by hook and crook, I have to make the special basis unavailable to Eve. So if Eve cannot do measurement, so here are splitting of information. If does not know which one is measured in 0-1 basis and which one is to be measured in plus minus basis. And that gives me the security. Okay. So since ultimately I am doing measurement in 0-1 and plus minus, so what is the need of creating an entangled state? So I can just start with 0-1 plus minus a sequence. So that's what DB84 protocol is. So I create a random sequence of 0-1 and plus minus. How will you create a random sequence? So it must be connected to a random number generator. We have already described quantum random number generator. So a random number generator gives, suppose in the string, the first two bits are 0, 0, then I make it 0. If the first two bits are 0, 1, I make it 1. If the first two bits are 1, 0, I make it plus. If the first two bits are 1, 1, I make it minus. So it's connected to a random number generator. I randomly prepared 0, 1 plus minus, and that string I send it to Bob. Bob does a measurement either in 0-1 basis or in plus minus basis. So what is it? So that means Bob puts in a beam splitter. So after the beam splitter, light may be reflected, light may be transmitted with the equal probability. So in the reflected side, he puts a setup for measurement in 0-1 basis. So if the 0 means horizontally polarized, 1 means vertically polarized, he just put a polarizing beam splitter followed by 2 detectors. And in the other path of the beam splitter, say transmitted path, he put a wave plate which gives a 45-degree rotation to the state and then followed by a polarizing beam splitter and 2 detectors. So randomly it will go in the reflected path or transmitted path, and if it goes in the reflected path, it will be measured in horizontal vertical basis. If it goes in the transmitted path, it will be measured in plus minus basis. So and then Alice and Bob compares where their basis matches, so they keep all those bits and forget about the rest of the bits. So in these cases, their result is expected to match. They must be correlated unless Eve is there. So they compare half of them and then find out whether there is an Eve or not. If the comparison finds that there is no error, there is no Eve. If there is a possibility of error, if there is an error because of the channel noise or because of Eve, then they do some privacy error amplification, error correction and such things and find out a smaller key at the end. So that's the basic of BB84. And then once the key is created, then you can encrypt things and send it through that key. So I'll skip certain things. So now in the morning I told you that there is a quantum random number generator. So this shows you a quantum random number generator available in internet, from which you can find out the random numbers, and then NIST test you can download and run. These are the tests for randomness, and you can check that whether the number is random or not. So now I was supposed to tell you how quantum is done in lab. So some laboratory items I have shown you. So I'll show you a setup which is a MSc PhD kind of training kind of setup. It's not a research level tool. So this is in our lab. So this is a third lab kit. So this kit, as one of this is Alice. So Alice has a laser source it creates, and here is a polarizer. So I download a quantum random number and decides that on the random number that I'll put it in 0 degree, 45 degree, 135 degree, or 90 degree. So then the light is coming in a horizontally polarized manner that I can adjust, and this adjusts the orientation, and then the light passes through. And here is again the similar polarization rotator, and here is a polarizing beam splitter. So this will be clear how we apply BB84. So once again, so this is the light source, this is a laser, and here this laser gives you horizontally polarized photon. So that adjustment I can do. Then there is a polarizing rotator which rotates it to 45 degree, 0 degree, 45 degree, 90 degree. Now I will decide this which one has to be chosen by depending upon a random number. Then I will apply this polarizer to move to a rotator. So the rotator can be 0 degree, 45 degree, etc. And 0 degree means there is no change. So if I give 0 degree and 90 degree here, then I keep it in 0 degree, and then this polarizing beam splitter will pass 0 degree horizontal polarized light, 90 degree will be transmitted, and this detector or this detector will click. If I create in minus 45, 40 or 45, I rotate it to 45 so that minus 45 becomes 0 and plus 45 become 90, and then I'll see this click. So this is if, but if does not know which way it is prepared. So if is doing this rotation randomly, but this is the setup of Bob also. So you look at this Bob setup. So by a random number, Bob is decided randomly using a quantum random number that whether he will put the polarizer in 0 degree or 45 degree. So whether that means whether he will do measurement in 0-1 basis or plus minus basis. So 45 degree will be plus minus basis, 0 degree will be 0-1 basis. Now, what this attack is doing, so if just replicating Bob, Eve is doing a measurement, and whatever output come, accordingly he was using a light source and making a copy. So you see that this part of the Eve is like Bob, and this part is like Alice. So this is a particular kind of attack happens in quantum. It's called measurement and resend. You measure whatever you got, you create and you resend. But that will lead to error, and then we can decide that what to do. So it's required a single photon source, but in this particular case, this we measured that this is not a single photon source. Now, this is what happens. Alice's basis is plus minus or diagonal plus plus. So this is 0, 1, this is 45, 135, and Alice's bit value is 0, 1, etc. Bob choose a basis. So when Bob and Alice's basis mismatch, that does not lead to a key. Only when their basis match, plus and plus, that leads to a key. So this is a raw key. So half of this we'll compare to find out whether eavesdropping has happened or not. And then rest half will be used like a key. Then there is a protocol called B92. So B92 is an interesting protocol. So instead of creating a random sequence of 0, 1 and plus minus, we choose two states. One state from 0 90 degree basis or horizontal vertical basis, and another state from 45 degree minus 45 degree basis or diagonal basis. So let's choose 0 and 45. And Bob does the similar things as before. But if Bob got 0, Bob will not be able to decide it is from 0 or plus. But if Bob got 1, then it is definitely not from 0, it is from plus state. And if Bob got minus, it is definitely not from plus, it is from 0. So then Bob can keep those states and forget about the rest. So shifted key is be created in that way, and then they can compare the half and decide. So this also you can do in the lab. So this is the actual setup. So this is the optical bench in our lab. So this is Bob. So you see Bob has two detectors. Here is a polarizing beam splitter. So this is what I was telling. So here is a rotator. So you download a random number because it's not connected to a random number. And if the and for doing this kind of experiments, you don't need actually optical bench. You got this kind of bench comes with the Thor lab, and you can use that. So this is a polarization rotator, and there are two detectors, and there are detectors electronics like this. So this is Alice. Alice has a horizontally polarization source, and depending upon random number, it decides that at to what angle the polarization will be rotated. So 0 degree means it will remain horizontal, 90 degree will make it vertical, minus 45 and will be by 135 degree, and so on. So after the similar setup is here. So it's just like Bob's setup is with Eve. So Bob is doing measurement before Eve. So Eve is doing measurement as if he is Bob and reconnecting that and then sending it to Bob. So this is how BB84 protocol, B92 protocol, there is some semi-quantum protocol and SARG protocol can be implemented using this setup. And this is a setup which you can have in your college. So this costs something like 3.5 lakh. But these are analogy kit, actual experiments, even much costly research level experiments, but this can teach much of the quantum mechanics. So if just check that whether sound is audible or not. So this is my Alice, this is Eve, and this is Bob, and we just tried to record for you and explain it. So I hope you understand how it works. So Alice's basis are random, then this key creates a shifted key, which is where the basis matches, and then we do some kind of error correction, and privacy amplification, and every step key size reduces. So I start with a 96-bit key and I end up with a 5-bit key. So this one I explained. So this is the setup for bomb testing kit or interaction-free measurement, a Michelson interferometer-based experiment. I explained it with the Mach-Zehnder interferometer, but I'm particularly stressing on this that using a Michelson interferometer, you can, and many of the labs have Michelson interferometer or laser-based Michelson interferometer. They can teach basic quantum mechanics using Michelson and Mach-Zehnder interferometer. So this detects the bomb. So I'll not explain these protocols. So I'll skip 2 slides. Okay. So the idea was to introduce you to lab. Means this Academies programs, people are supposed to go to lab, but here we cannot go to lab. And then I was expecting that in lecture of Professor C.M. Chandrasekhar, you will have some exposure of the IBM quantum computer, but he talked about more sophisticated simulators. So I thought I'll show you some simple slides. And in continuity with what I told you in the previous lecture, that when I was a student, I had to believe my teacher that collapse on measurement happens. But can you see that collapse on measurement happens? Can you see that quantum mechanics is true? Of course, you have to believe that IBM is really doing in quantum computer, but you can throw chalk from your phone and check. So you have to make a login in IBM quantum experiment. So you go to this site or just write in Google IBM quantum experience, and with your Gmail, you create an ID. So this is, you write your Gmail ID and create a password. So this is hands-on an IBM quantum computer. It's pretty sophisticated now, but I'm just the most thing. Then you reach IBM quantum experience, and in the right-hand side, you will see the gates, which I have mentioned. So you can drag and draw, and you can choose that which IBM quantum computer you are working. And its architecture is given. So this one, what this rows means that this can be control, this can be target, this can be control, this can be target, and this kind of things I have already explained. So in your user account, I'll not explain. So this I have already explained the Mach-Zehnder interferometer. That one is 100%. So I want to create this Mach-Zehnder interferometer, say in IBM quantum computer. So here are the gates. I have to do drag and draw. I have to put a Hadamard and another Hadamard and check what happens. So these are the different gates. So I mentioned that T gate and S gates are a specific type of phase gate. So phase gate has e to the power I phi here. So when phi is equal to pi by 4, it is T. You take a dagger, this becomes T dagger. You make it pi by 2, this will become I. You make it pi, this will become -1. So S is P pi by 2, phase gate of pi by 2. This is phase gate of pi. This is phase gate of pi by 4. This is 0. So we did a couple of experiments. So this is the experiment where is the Hadamard gate and then Hadamard gate, and this U1 is your phase gate. So I apply a phase gate and I give different values of phase, pi by 8, 3 pi by 4, 3 pi by 8, and I find out the probability of measurement of outcome 0. So what do you expect? So I already mentioned that if you have a Mach-Zehnder and you put a phi here, then the probability of clicking this detector will become cos square phi by 2, and this will become sin square phi by 2. So these are my calculations if the wave theory is correct, that particle become wave or the photon goes in 2 paths. But now I did this experiment. So this is just like an experiment you do in the lab. In an IBM quantum computer, you give a Hadamard, you give a V1, you give Hadamard, and do this experiment. And when you do this experiment, you note these values 0, pi by 8, pi by 4, 3 pi by 8, and so on. And then these are the values which you are giving by hand, and this is your lab report. See that when the phi is small, the probability of detecting 0 is almost 1, and then gradually it is reducing, and then again it is increasing. So I plot that, and this is the theoretical plot, cos square theta by 2, and the yellow one is the experimental plot, and you see that how well the theory and experiment matches. So this shows that quantum mechanics predictions, a quantum mechanical Mach-Zehnder interferometer, you can do using your mobile phone also. Means the Android phone, you can throw this job and you can do quantum experiment. So I would prefer that if it was a classroom thing, that you should all start with your your thing, and somebody will do it for pi by 8, somebody will do it by pi by 4, and we should have created this in the classroom itself. But hands-on is hands-on, so I will expect that in the evening you all will try and reproduce this kind of thing. Now, you think of a simple Hadamard. This is the simple most experiment which you can do in IBM. So you take a simple Hadamard and you have a get 0. So what this 0 will go? This 0 will become 1 by root 2 0 plus 1 by root 2 1. And then you do a measurement. So it will collapse sometime to 0, sometime to 1, and nobody knows where it will collapse. But if you just run one time, if you run 8,000 times, then 4,000 times roughly it will be in 0, up to 4,000 times it will be in 1. So we check that. So you can do that in IBM quantum computer. So you can choose the number of run or number of shot. So we choose one time, it clicks in 1, which has another time it becomes, so this becomes 0, this becomes 1. So it is random. Then we run 1024 times. And then I see that 0.576 is the probability of getting it in 0, and 424 is probability of 1. So it's not really 0.5. So we went up to 8192. That is the highest number you choose. We can choose in IBM, but still it is not half of. So that means 8192 is not a statistically large number, but it's almost half of, but it's not really half. Now, how to draw this circuit? So one thing is to draw it by drag and drop, but you cannot handle big circuits in that. So there is a programming language. So now most people write it. So there was a Quasum window where you can write it by hand. So when you write QRG by 5 means it's a 5-qubit register, quantum register, and C register C5 creates a 5-qubit. So what are those 5 qubits? 1, 2, 3, 4, 5, which marked at Q0. These are the qubit line. Now you write where you have to put Hadamard. So you write H Q0, that puts the Hadamard in the line Q0. Then you write CX Q1 Q0. So 1 will be the control, 2, 0 will be the target. So it's a control in 1, target. So that's how you can write C0. And then you write measure. So which one you measure first? Q0 goes to C0. So Q0 you measure, and that takes you to classical registers. Q1 goes to, again, C1. This leads to a classical register. So you can write a program. You people can learn Qiskit. Many people may know Qiskits, and that's very interesting that you can search many things. So I'll not. So this quantum computer we have already described, and Vijay is trying to make similar quantum computer, and he explained how those quantum computers are. So this is the architecture of 16-qubit quantum computer. And in the last class also, last to last lecture, my first lecture I mentioned that a C0 can be converted, and it's required because you can apply between Q2 to Q1. Q2 is control, but Q1 is control, Q2 is target is not allowed. So if you need that, then you have to invert. So how we do the inversion? Inversion is done in this way, that this is equivalent. So in many circuits, you will see this kind of block. So for example, it's a swap gate. So it's a C0, opposite side C0 and C0. So this opposite order C0, that this one is control, this one is target, is now inverted by applying 4 Hadamard gate. We mentioned about error correction. So yesterday, Vijay also told about error correction, that unless error correction was possible, quantum computing would have been impossible. So this is a very important thing. All the classical computer works on digital computation, because digitally, suppose there are 2 distinct states which are 0 and 1. So if I raise my hand and it's called 0, and if I down my hand, it's called 1. So if the hand is not completely, it's like this, you know that it's close to 0, you can correct and make it 0. But analog computation, this is also, in analog computation, this is 0, and this may be another signal. So I don't know it's another signal or it's just error. Because of error, 0 become this. So error correction become impossible. And here alpha and beta is continuous. So people initially thought that error will not be able to error correct in quantum computing, but later people realized that error can be corrected and using majority voting techniques. So I'm not going in description of that, but this is an error correction circuits, and this kind of things you can implement. So I give you a perception of how we do cryptography in the lab, how those things can be implemented in small scale labs which PG departments can afford, and how IBM quantum computer based experiments can be given, and things like that. So now whatever I want to tell you formally and give you an exposure of lab kind of things means that's done, and it's open completely for discussion, interaction. In the discussion is not restricted to my lecture only. Means anything you want to ask means on the applications or core quantum mechanics or in general any. So it's open for everything.
So you can either write your questions in the chat box or you can directly ask also.
So are there students in the, if there are students in the audience, means there are many vacancies at the moment for junior research fellowship and research associates under Quest scheme, because we all received the money about 2 months back. So most people have advertised, and there are many advertisements on information related things for research associates and JRF. You can look at those possibilities also. No response? No query?
No choice.
A very good evening to everyone. Kudos to all the organizers. It was really indeed a very interactive and very useful sessions from the very beginning until to the advanced applications. I would like to ask for the undergraduate students, how can they be exposed to this field? One last application which you showed was really very useful, which everyone can try. But otherwise, for undergraduate students, what would you recommend?
Okay. So I actually wrote many papers with undergrads. So I showed in the in my first lecture about a bail state discrimination scheme. So Professor Panigrahi of ISAR Kolkata, and I wrote it with a BTech third year student, and then it was experimentally verified IISc. So there are certain things. These gates are just like a matrix, and you don't need the deep understanding of quantum mechanics, perturbation theory, particle physics, and such things for doing quantum logic, and those kind of things students do very well. So for example, you want to play with IBM quantum computer, realize some circuits, and say, with a BTech now we have done something on quantum game. So they applied some prisoner's dilemma game, and then Marvin inequality. So there are many things which is well studied, and they can think, they are very creative. So this is a field where undergraduate students, and especially not only from BSc physics, but from the BTech background also, they do very well. And there is another question which I answered in this. So you cannot do quantum computing using C or Python. So what you can do, the way I have written these matrices, you can do those matrices. And once you write these matrices, you can multiply. So matrix multiplication can be done in any language, whether it's Fortran, whether C or Python, does not matter. But most of the I write in MATLAB or Mathematica. But there is a nice, if you go a little deep into the physics, there is a nice code nice toolbox called QT, QU for quantum and TIP. So that works on Python, and QTP is pretty good. It's a very nice toolbox, but that has a flavor of quantum optics also, and many things can be done, including the Lindbergh equation, which is written, can be solved there. Jens-Cummins model can be solved. Then there is a question, is quantum communication is still on research level in the world? As Indians, where do we stand? Okay, there are many books. So you can read my books also, which is pretty elementary. Then you can read Mac Mohan. Mac is not MAC, it's Mac MC and Mohan. Mac Mohan is a nice book. Then there is a book by Phillips and Kai, which is easy to follow. But once you follow this easy book, there is a Bible of our subject that's called Nielsen and Chuang. So Nielsen and Chuang is the best book to read, but not to be the first book to read. And is quantum communication still on research level in the world? So I have already mentioned that IT Quantic sells several solutions. There are many solutions which are in market, commercial solution. In India also, QNew Lab sells commercial solutions. But It does not mean that. Means a car is already in the market, does not mean that research does not happen on car. So, there are many people who work on the development of engines and other things in the car. So, commercial solution is there and the research is also there. So, as far as Indian research is concerned, so in India, from the beginning, there were people interested in quantum communication and things like that. So, many of this no-go theorem, so this no broadcasting theorem, no deletion theorem, this has one Indian author in that. It is Arun Pati from HRI. So theory we were strong always, and experiment require a lot of money. So you get some exposure like the lab of Vijay where experiment is done. So you have already seen in yesterday's lecture that you have already a lot of people who work in this field. So some are experimentalists, some are. Chandrasekhar is now establishing a lab. We started as a theoretician, but with the pump of money in the quest, we are also doing experiments. So experiment probably we are not many group, but in theory we are at par with the world. So Anirudh Chaudhary wrote that he want to ask something. Please ask. Unmute and ask.
Sir, good afternoon, sir. I want to ask that I am first year grad student from Delhi University, and sir, what can I do? Means I am doing physical science, BSc physical science, and sir, I want to pursue particle physics in future. Sir, are there any guidelines from you that I should do?
Yeah, what was your last sentence? You want to pursue?
Particle physics.
So, at the moment you understand your basic means as good as possible, and then there are two windows. Means like in Delhi University, the particle physics is very good. Means then you can continue your MSc in the main campus. You can talk to people like Debojyoti or Patrick Dasgupta. Means there are many good particle physicists in your campus. But first you have to do BSc very well so that you get a chance in MSc, and then at the end of BSc also try for appear in JEST and give IISc's entrance for integrated PhD, appear in JEST and try to join PhD program of HRI and other places as extraordinary BSc, the integrated PhD program. So there is a window for joining PhD after BSc through JEST as extraordinary BSc. But first you have to establish that you are extraordinary BSc and concentrate on your BSc text and do it as much as possible. Basics has to be improved and fundamental has to be clear.
Okay, sir. Thank you.
There is integrated PhD in TIFR and IISc.
So if you have questions in the morning on the morning sessions or questions directed to Professor Misra, you can also ask those. Means it's not restricted to this talk. That's what I told in the beginning. Any questions and the whole conference, means you want to ask anyone, me or Professor Misra, you can ask now.
Sir, did we ever try to control the nature of matter? Means wave nature and particle nature. Did we ever tried?
I'm not clear what you mean by that, but it's not your choice, it's in nature. But you can decide what you want to see. It's which property you want to see, that you can decide your detectors accordingly.
Okay, sir.
But there are means like conventionally till few years back it was believed that either you see wave nature or you see particle nature. You don't see both. So that's why in a single manifestation you will not see both. But Heisenberg's uncertainty principle tells you that you cannot see them with arbitrary accuracy. So with doing weak measurements, means not a strong measurement. I will not use the word weak measurement because that has a specific meaning. So with inaccurate measurement, you can have now both the properties simultaneously also.
Thank you, sir.
Sir, there is another question. What kind of data rates does quantum cryptography
No,
require?
data rate is not a meaningful word. So rather, it's a meaningful word is a key rate. So what is the key generation rate? Means I'm creating a random number. So to encode anything, to encode anything, I require a key of the same size. So if you want to send an encrypted data, so whatever is the data size, you need the key size. So whatever is your data generation rate, so you must have key generation rate or previously occupied key, previously captured key, means you have prepared key and it's already with you. So you don't generate the key always in the real time because error correction takes some time. Key generation rate can be in Mbps, but it depends on what is the distance. So the higher is the distance, the lower is the key generation rate. So with the distance, it decreases. It's like if you want to do it 200 kilometers, then the key rate will considerably decrease. So it will go in few hundred kbps, but when you want to do it in your lab setup on half a kilometer or 1 kilometer, it will be in Mbps.
Anuradha ma'am has also joined. If you people have some questions from her also, she is also ready to answer. Sir, if there are no questions, can we convert this? There is another question. Can we introduce quantum communication at BSc level or BSc physics?
Yes, of course, means that, but if you have freedom to do that, means like, means in, as per as means National Academy of Sciences Delhi chapter is concerned, means we frequently organize student workshops and we have many times we have taught quantum communication and these things to undergraduate students of Delhi University and nearby institutes, and they can really follow. And like we teach elective on quantum information to our undergraduate students. It's elective, but they can follow, and so it's not. I mean, it can be introduced in that level. I mean, there is no problem in that.
Sir, if there are no questions, in fact, we had invited our principal to join us during the valedictory function. But just now I have got the message from him that he will not be available due to some pre-engagements or some is busy. So can we convert this into a valedictory function?
That makes sense. And then instead of joining once again means.
Yeah.
So
I will request Dr. Satyaprakash Singh to begin the proceedings of this valedictory function. Because Dr. Anuradha Misra is also there and Sajid also there. Dr. Satyaprakash Singh.
Okay. Thank you, sir. So good evening to all of you. Respected Dr. Anirban Pathak, respected Dr. Anuradha Misra, distinguished faculty members, delegates, and my dear students. I, Dr. S.P. Singh, welcome you all to the valedictory function of the 3-day Science Academies virtual lecture workshop on elements of quantum information. First of all, I would like to request our co-ordinator of the workshop, Dr. R.K. Dwivedi, sir, to present a brief report about the workshop. Dwivedi, sir.
Friends, quantum physics is well known to all of us. I remember when I was a student, I was taught quantum mechanics, and the same is being taught these days also. Quantum mechanics is not an easy subject, as there are several ways of describing it. This workshop has given all of us an opportunity to learn quantum mechanics in a very systematic way. That is why quantum mechanics, starting from black body radiation to photoelectric effect, Compton scattering, wave particle duality, matter waves, formulation of new theory through thought experiments, Heisenberg uncertainty principle, Stern-Gulls experiment, linear vector spaces, linear operators, eigenvalue problems, operator and observables, their measurement and expectation value, time evolution of wave function, superposition principle, commutator, orbit and spin spaces, Pauli matrices, unharmonic oscillator to Bell works on hidden variable theories. All these topics were very well described in the 6th lecture by Professor Anuradha Misra ma'am in the morning session. Coming to the quantum applications, these are really very important to all of us. This workshop has given an opportunity to learn exciting applications of quantum mechanics, such as basic building blocks of a quantum computer, that is qubit, due to quantum superposition different from classical bit 0 and 1. One qubit gate, Hadamard gate, H is 1 by root 2, 1110 minus 1. 2 qubit controlled not C not gate, which can be implanted directly in IBM quantum computer. Also, these qubits are realized using Josephson junction or superconducting qubits or unharmonic oscillator. Then all these quantum gates can be put together to form a circuit, and the circuit together makes a quantum computer. Coming to quantum communication takes the advantage of laws of quantum physics to protect data by a process called quantum key distribution and quantum network. Quantum communication is considered unhackable and therefore future of secure information transfer for banks, power grids, etc. and etc. Coming to quantum simulation makes use of quantum physics to develop tools for solving challenging problems in basic sciences where quantum effects are involved. It is based on quantum superposition, quantum interference, and quantum entanglements. A large number of quantum systems in condensed matter physics, high energy physics, atomic physics, etc., such as neutral atoms, ions, polar molecules, nuclear spins, superconducting circuits, electronic spins in semiconductor, etc., have been proposed for quantum simulation. We came to know about digital and analog quantum communication and how they are different from each other. Coming to quantum cryptography, we come to know about communication using secure methods. And in the last lecture by Professor Anirban, we got the idea of quantum cryptography through several algorithms like source algorithm, Grover's algorithm, and then he demonstrated the quantum cryptography analog demonstration kit by exploiting the well-known Mach-Zehnder interferometer and Michelson interferometer, which are the part of every MSc lab, I suppose. Then we had basically a hands-on with IBM quantum computer. I think since we are in the virtual platform, would it have been a real platform, I think we would have enjoyed all these things in front of Professor Pathak. But anyway, we have the flavor of all these things, and maybe I'm sure that some of the participants in the future will have all these things to work with. So apart from this, we had a special lecture, and that special lecture gave us an opportunity to learn about negative refractive index metamaterials and how can we exploit them for controlling the IR absorption and emission. The workshop has given a nice opportunity to all the participants to learn exciting fields of various quantum applications and metamaterial application. I am sure that some of the student participants will definitely choose to pursue research in this field, and this workshop has enriched all the teacher participants not only to learn quantum mechanics basics but also to include these in their curriculum. I thank Professor H.S. Mani sir, the course director, Dr. Anirban Pathak and Dr. Anuradha Misra from the core of my heart for their wholehearted support to bring this workshop a reality. I express my heartfelt gratitude to Professor Aditi Ray, Professor C.M. Chandrasekhar, Professor R. Vijay Raghavan, and Professor S. Anant Ramakrishna for enlightening us on the exciting applications of quantum mechanics. I thank all dear friends and students participants who have joined this virtual platform from morning to evening in spite of several problems of internet connectivity, etc. I have talked to several of my students. They have several times complained that 1.5 GB data is basically used in one lecture or 1.5 lectures only, but still they are managing all the lectures. So I am thankful to each and all. Thank you very much for joining this workshop. Dr. S.P. Singh.
Thank you, sir. It is time now to get the valuable inputs about the workshop from the participants. I invite Dr. Sanju, faculty in physics, Miranda House, New Delhi, to share her views about the course with us. Dr. Sanju.
Thank you very much, sir, for giving me this opportunity. I would like to use this opportunity to thank the organizers for their thoughtful planning and efforts to bring renowned expert on this platform. The outcome is commendable. And people like me were reading articles on quantum information here and there, and were having a very blurry picture of the field. And this 3-day workshop has really helped in connecting the dots. And all the lectures were really excellent. They were full of information. I would like to thank specially Anuradha ma'am for sparing so much of time and putting very important concepts together in just 6 lectures. She has been very patient throughout. And I would like also to thank Professor Pathak for giving overview of the subject, or the recent trends in the field, and the detailed explanation of quantum gates and quantum cryptography. And overall, this workshop has really helped in brushing the concepts, bringing fresh perspective to the concepts, and has been really informative on recent research going in the field in India and in general. It was really nice. Thank you very much. And thanks for providing the recording in case we have missed something, and for the students also. Thank you very much.
Thank you, Dr. Sanju, for such a nice input. Now I invite Dr. Pooja Goel, faculty in physics from Govind Ballabh Pant University of Agriculture and Technology, Pantnagar, Uttarakhand, for her valuable inputs. I think that Dr.
In fact, Dr. Pooja Goel is on the way. She is not available on this virtual platform. So she has written an email to me. I have received it just now, so I will read it. Thank you so much for organizing such a wonderful workshop on elements of quantum information. Dr. S.P. Singh and Dr. Manoj Kapoor sir conducted the session very well, and the best thing is the time management during the sessions, which normally people don't care about. I have attended all the lectures by Dr. Anuradha Misra ma'am and Dr. Anirban Pathak sir. I missed a few lectures in the afternoon session as we have semester examinations going on. Please convey my message to ma'am, as she is the first lady whom I have seen teaching such a dry topic with most soothing smile on her face. I like the way she introduced the quantum mechanics through thought experiments like bullets, water waves, and electrons. If we were able to grasp the conclusion of this thought experiment, we can easily understand the 2 most important founding pillars of quantum mechanics, that is de Broglie hypothesis and the uncertainty principle, which are normally understood as 2 different concepts by the beginner. Thank you so much, sir, for allowing me to be the part of this workshop. Regards, Pooja Goel.
Thank you, Dr. Pooja, for your nice comments. Now I'd like to invite Dr. Tejas Tang from ISER Bhopal for his views on the workshop. Dr. Tejas is there? Are you listening?
Yes. Hello.
Okay.
Hello.
Okay.
Thank you very much, sir. First of all, I congratulate to famed and oldest institute of India, Christchurch College, Kanpur, and of course, I congratulate to Professor Mani, sir, the designer of this workshop, Professor R.K. Dwivedi, sir. With Dwivedi, sir, I have been associated since 7 years when I doing PhD in Barkatullah University, Bhopal. And of course, he is my teacher because I learned so many practicals.
Feedback link share.
And SP Singh sir and all team members to conduct such a useful and informative workshop. I noted few points, sir, which I want to share with you. Actually, sir, this type of school I attended first time. And all speakers during course were subject expert and keynote researcher in their research area. And definitely I said this workshop has given opportunity to students and also researcher to motivated them for doing research in quantum computing. I mainly noted that the speakers started the talk from the basic root and then they have completed. That means जैसे हम कहते हैं कि
सर फीडबैक लिंक चला गया ठीक सर ठीक सर thank you Tejas. This is to inform the participants that we have sent the feedback form link in the chat box. Okay, please fill that feedback form to get the certificate of participation. Now, I'd like to call upon Bhavya Bhatt for her invaluable insights about the course. Bhavya.
Yes, sir. Good evening to all the respected teachers, invited speakers, and my fellow participants. It's been a great privilege to be a part of this 3-day virtual workshop on elements of quantum information. Speaking about my personal experience about this particular workshop, I felt the workshop was of great use as it helped me to get into the fundamentals as well as the upcoming trends in the field of quantum mechanics. The knowledge imparted here helped me to revise my basic concepts of quantum mechanics. The ideas regarding quantum gates and quantum computers were new and interesting to me. I also enjoyed learning about the concepts of quantum cryptography. Overall, I felt the sessions were of a source of great knowledge and information about the discoveries in the field of quantum mechanics. And also, I look forward attending more of such sessions in the coming future. Thank you.
Thank you, Bhavya. Now, I'd like to invite Himanshi Dwivedi for her inputs about the course. Himanshi.
Thank you, sir.
Himanshi, are you there?
Honorable resource persons. Okay. Yes, sir. Am I audible?
Okay. You are audible.
Okay.
You are audible, Himanshi.
Honorable
Go ahead.
resource persons. Thank you, sir. Honorable resource persons, respected professors, and all the participants, very fine good evening to all. It is indeed a pleasure and an honor to have this opportunity to revisit the 3 days of Science Academies virtual lecture workshop on the elements of quantum information at the Department of Physics, Christ Church College, Kanpur. On 12th March, the workshop had a formal start with the inaugural function hosted by our college. This was succeeded by the first lecture of the session, which was delivered by Dr. Anuradha Misra ma'am, professor and head of department at the University of Mumbai. She initiated with the basics of quantum mechanics so as to provide a level playing field to all the participants. Say, for instance, the photoelectric effect, the Compton scattering, some thought experiments, wave particle duality, etc. In the lecture 2 slot of the day, Professor Misra continued with the Stern-Gerlach experiment and the concept of polarization. She also demonstrated the connection between quantum mechanics and linear algebra. Next lecture session was graced by Professor Anirban Pathak sir from JIIT Noida. His presentation acted as a smooth bridge between the first 2 lectures and the lectures that were yet to come that day. He gave an introduction to quantum gates, quantum circuits, and quantum computers. Professor Pathak had put forward the concept of classical reversible gates, classical irreversible gates, and quantum gates, which are essentially reversible. Polymatrices were presented as quantum gates. Also, we were made familiar with some of the 2-qubit gates. Professor Pathak had an interactive session where the participants were encouraged to solve quantum circuit model. Next, we had an enlightening lecture by Dr. Aditi Sen Day ma'am of HRI Prayagraj on quantum communications. Professor Day had convincingly advocated the advantages of communication systems built using quantum physics over classical protocols. She commenced her lecture from the most basic introduction to communication, and she effectively explained the classical information transmission and quantum state transfer using the 2 characters, Alice and Bob. Professor Say nicely presented how classical world allows only distinguishable or orthogonal states and quantum world permits non-orthogonal states in addition to orthogonal ones. Certain experimental progress with photons and ions was also discussed. We were also made to understand quantum teleportation. Ma'am also highlighted how no faster than light communication is ensured and no cloning theorem is kept in check. Overall, it was a wonderful lecture. We had Dr. C.M. Chandrasekhar sir from IISc Bangalore for the lecture number 7. He presented a talk on quantum simulations. He discussed quantum superposition, quantum interference, quantum entanglement. Professor Chandrasekhar made us aware of the various interdisciplinary applications of the topic as well. It was such a nice presentation. For the next lecture, we had Dr. R. Vijayaraghavan sir from TIFR Mumbai as our resource person. His topic for the presentation was how to build a quantum computer. His lecture commenced with the explanation of qubit, the information that can be stored in one qubit. He then proceeded with quantum algorithms, introduced single qubit gates and multi-qubit gates. He also touched upon the challenge that the qubits are not stable, which was discussed later in the lecture. He went on to share several applications. Overall, the lecture was so engaging. The last session of the day was a special lecture by Professor S.A. Ramakrishnan sir, Professor of Physics at IIT Kanpur and Director of CSIR CSIO Chandigarh. Sir picked up with the light and electromagnetic radiation, gave an introduction of infrared light, infrared bands, the atmospheric transmittance, and the air glow in the night sky. Image intensifiers for near-infrared light were discussed. He explained mid-infrared images, long-wave infrared images. Usefulness of IR imaging for military was also made evident. Metamaterials and its applications were discussed extensively. Now the third and final day of the workshop, that is today, began with the two generous lectures by Dr. Anuradha Misra ma'am. She enlightened us with the variational principle for a two-level system and applications to hydrogen atom, harmonic oscillator and n-harmonic oscillator. Professor Misra also gave us insights into Bell's work on hidden variable theories and Bell's inequality. The final presentation of the workshop was given just very recently by Professor Anirban Pathak sir. It was about an introduction to quantum cryptography, where we stand, how we perform quantum cryptography in the laboratory. With this, we come to a pause and not an end to our 3 days virtual lecture workshop. Because such workshops never end, they incite and inspire young learners. So this has not been only an educational experience, but it has inspired many of us. Thank you all.
Thank you, Himanshi, for such nice views and summarizing the things that we have experienced for the last 3 days. Thank you, Himanshi. Anuradha ma'am, are you there? Are you listening? I am not seeing you there.
Yes, I'm
okay.
here.
Okay, ma'am. Okay, ma'am. So I invite you most cordially, ma'am, to share your experience about the workshop with all of us. Anuradha ma'am.
Dear Dr. Dwivedi, Dr. Singh, and all the faculty members of Christ Church College, I congratulate all of you for organizing this very, very successful workshop. As has been said and as we knew from the beginning, the workshop was planned very nicely. All the lectures and lecturers were selected very appropriately, and the whole program was very well crafted. The organization was very good. As somebody said, it was the time limit was well taken care of, so that there was proper progression of the workshop. The morning theory lectures and the afternoon practical sessions were planned beautifully, and all the lecturers gave very good lectures. I myself enjoyed the afternoon lectures, whatever I could attend. And I hope that the participants have also benefited, as we can see from the feedback. I hope people are going back richer in knowledge and with a lot of enthusiasm to try this very, very exciting new field of quantum information theory. I want to thank the organizers and Professor Mani for giving me this opportunity to take part in this workshop. And I hope to keep in touch with all of you, all the participants and the organizers, and have many more such programs in future. Once again, thank you very much.
Thank you, ma'am. And I'm sure that we all get benefited with your vast knowledge about the subject, especially our student participants of this course. Again, thank you, ma'am, for being with us. Now I would like to invite Dr. Anirban Pathak, sir, for his invaluable concluding remarks.
So, I have spoken a lot just now, means there is not much to tell, but I was expecting more interaction, more questions. So, I mean, the program went well, everybody spoke nicely, but it was supposed to be interactive and the interaction was less. So, everybody tells the good thing, means I'm going to become devil's advocate. And initially, and every day means today it's not an exponential decay, but every other day there was an exponential decay in the participation. And by the time Anant was talking yesterday, it reduced to 40. It's Aditi's time also. So it was, the number of participants was decaying in the evening and there was hardly any interaction. So that was not expected because it requires a lot of effort to plan this thing, to design the lectures. And so Professor Mani worked a lot, Professor Dwivedi worked a lot. Means it's a 2-3 months interaction planning in establishing the connection, the sequence. And so if you miss a lecture, then it's very difficult to connect with the other lecture. So for example, suppose somebody does not attend the quantum gate lecture and then suddenly he comes in the next day on quantum computer lecture of Vijay, then it will be very difficult to follow. If you don't attend the lecture on bracket and then you are in another lecture where bracket is used. So this is again just like a feedback you were giving for us. Means I'm also giving feedback to the participants that if you attend a course, means try to attend all the lectures. So skipping lectures does not make much sense because then the other lectures does not remain useful. So saying so, but even if in no workshop expect that everybody will follow and continue. But if 2 people continue, 2 of the undergraduate students continue in the field, 4 faculty member goes back and whatever they have learned dissipate among their 40 students, then the workshop will be considered to be successful. And I hope at least that will happen, that some of the faculty member will share the know-how they'll earn from here with their students who are not present here. Some of the students who are present here will continue this and share the things they have learned with their friends. And sharing of the knowledge will make the workshop allow the workshop to reach to more people, and that will be the use of the workshop. And stay in touch, means I have given my phone number and email in the beginning. So preferably if you have query, means you read something else and then still you have query, you can drop me a mail. And it would be dishonest if I don't thank Professor Dwivedi for planning, organizing, and all the efforts he did. And initially, before the workshop, I was familiar with him only, and then in the workshop, I recognized that all the entire team, the department was active, and at least the people from the department, Professor Singh and others, were present in all the lectures. And attending all the lectures is not easy for faculty members, and especially when you are in station, there are so many administrative jobs and other things. So I'm extremely satisfied, and I would prefer to be present physically in the Christ College. Actually, the professor who sits next to my office is also R.K. Dwivedi. So he's a material scientist and he's from Christ College. So I knew about your place, and it's a great pleasure to be associated with a place which is established in 1866. And I wish the students who are there are familiar with the long heritage of the college and will do something which makes the college more proud. So those who are studying in this college, they have a great responsibility to do better and achieve the feats which their seniors have achieved. So I'll stop here. Altogether it was a wonderful workshop, and all the people who organized it deserves thanks. And of course, the participants were still now attending it. So most of my comments of decaying participations are for those who were not physically present. Okay, I'll stop.
Yeah. Thank you, sir. Without your help, I must say that it is not possible for us at all to organize this workshop. Your timely inputs and constant guidance help us a lot in conducting this program. Thank you, sir. I take this opportunity to thank Professor H.S. Mani, who due to some unavoidable reasons could not attend the workshop. But sir, we always feel your presence, and without your inspiration and motivation, it is impossible for us to organize such a big event on the virtual platform. Thank you, sir. I would like to thank all the resource persons for sharing their valuable knowledge with us. I would like to thank our Secretary, Reverend S.P. Lal, Principal, Dr. Joseph Daniel, and all the faculty members for their support and encouragement. I would also like to thank the participants for attending the workshops, and special thanks to our technical support team, especially Athar Rashid, for providing all the technical support. With this, we come to the end of the valedictory function. Thank you for being with us for the 3 days. We share a lot, and in near future, we hope that we have the interactions, fruitful interactions with you all. Thank you once again. Take care and bye.